Right now, tonight, while you are watching this, someone somewhere is stealing secrets they cannot read. Encrypted files, diplomatic cables, medical records, banking data, military communications. They are copying them quietly from networks around the world and storing them in vast, humming archives. To the thieves, it is all meaningless. Every file is protected by encryption, mathematics that scrambles information so completely that even if every computer on Earth worked together for longer than the universe has existed, they still could not unlock a single message. So why steal something you cannot read? Because the thieves are patient, and because they are making a bet. Intelligence agencies have a name for this strategy. They call it harvest now, decrypt later. Governments, including the United States government in official policy documents, have openly warned that adversaries are collecting today's encrypted secrets while waiting for a machine that does not yet fully exist. A machine powerful enough to turn the mathematics protecting almost everything, your bank account, your private messages, the power grid, and even diplomatic communications, into an open book. A global race is already underway. The world's most powerful nations are investing billions of dollars to build a machine unlike anything humanity has ever created. That machine is a quantum computer. And here is the first surprising thing about it. It is not simply a faster computer. It is not a better chip. It is not a bigger data center. And it is not just a smarter program. It is an entirely different kind of machine. Instead of following only the familiar rules of ordinary computers, it works using the strange rules that govern atoms, electrons, and light. Those rules are so surprising that when scientists first discovered them more than a century ago, many of them spent the rest of their lives arguing over whether they could possibly be true. One of those machines is running right now. It hangs upside down inside a laboratory. From the outside, it looks like a giant chandelier made of gold-plated copper and silver. Layer after layer narrows toward a tiny chip at the bottom, no bigger than your thumbnail. Around that tiny chip, engineers maintain a temperature almost 200 times colder than the empty darkness of deep space. As far as we know, it is one of the coldest places ever created anywhere in the universe. Not because cold makes the machine faster, because cold makes it quieter. Quiet enough to detect something almost impossibly delicate. A piece of information that is not simply zero, not simply one, but a precise and fragile combination of both at the same time. If that sounds impossible, good. Hold on to that feeling, because more than 100 years of incredibly precise scientific experiments all point to the same conclusion. This is genuinely how our universe works at its deepest level. Albert Einstein never accepted it. He famously described part of it as spooky. For nearly 30 years, he tried to prove that it could not be true. He never succeeded. And today, the very ideas he challenged are becoming the foundation of a new technology. Over the next few hours, this documentary will answer 3 important questions. First, why do we need a machine like this in the first place? What limits has ordinary computing reached, and why can we not simply build bigger and faster computers instead? Second, how can a machine based on quantum physics actually work? What is really happening inside it? We will build that understanding from the ground up, assuming you are starting with no prior knowledge. And third, what happens if this technology succeeds? What could it mean for your privacy, for medicine, for energy, for global security, and for the balance of power between nations? And just as importantly, what will it never be able to do? Before we begin, there is one promise. Quantum computing is surrounded by enormous excitement. It is also surrounded by deep skepticism. Both have misled intelligent people. So throughout this documentary, we will follow one simple rule. Whenever we cross the line between established fact, demonstrated engineering, and informed prediction, we will tell you. Facts will be presented as facts. Engineering achievements will be presented as achievements. Predictions will be presented as predictions. Nothing will be made to sound more certain than it really is, because the real story does not need exaggeration. The real story is extraordinary enough. We are living through one of the greatest scientific projects in human history, an attempt to take the deepest and strangest layer of reality, the very layer Einstein could never fully accept, and transform it into a practical tool. But to understand how anyone even imagines something this extraordinary, we have to go back, not to a physics laboratory to a loom. Chapter 2: The Machines That Built Our World. In 1804, inside the silk workshops of Lyon, France, a weaver named Joseph Marie Jacquard revealed a machine that seemed almost magical. His loom could weave incredibly detailed patterns, flowers, portraits, even entire scenes, with very little human guidance. Its secret was surprisingly simple. A chain of stiff paper cards, each punched with tiny holes. Where there was a hole, a hook passed through and lifted a thread. Where there was no hole, it stayed in place. A hole or no hole. Yes or no. 1 or 0. Without realizing it, humanity had stumbled upon an idea that would shape the next 2 centuries. A long sequence of simple yes or no choices, arranged in the right order, could represent almost anything. A flower, a piece of music, and eventually, even the instructions needed to operate a machine. About 30 years later in London, a brilliant and famously difficult mathematician named Charles Babbage saw those punched cards and imagined something even bigger. He was designing a machine called the analytical engine. It was a room-sized machine made of brass gears built to perform complex calculations. Then Babbage asked a remarkable question. What if those punched cards could feed the machine not only numbers, but instructions? What if a machine could be told what to do? What if it could be programmed? Babbage never finished building it. The engineering of the Victorian era simply was not advanced enough. But someone working alongside him understood the true importance of the idea even more clearly. Her name was Augusta Ada King, better known as the Countess of Lovelace, or simply Ada Lovelace. She was the daughter of the poet Lord Byron and a gifted mathematician in her own right. In 1843, she published a set of notes describing how the analytical engine could follow a series of instructions to calculate numbers step by step. Today, those notes are widely considered to contain the world's first published computer program. But Ada Lovelace saw something even more extraordinary. She realized that if a machine could follow instructions to manipulate numbers, then one day it might also manipulate symbols of any kind. It might even compose music. More than 100 years before the first modern computer existed, Ada Lovelace had already imagined what computers could eventually become. Then the idea seemed to disappear. For nearly 90 years it waiting for 2 missing pieces, a mathematical soul and an electronic body. The mathematical soul arrived in 1936. It came from a quiet young mathematician at Cambridge named Alan Turing. While studying the limits of mathematics, Turing imagined an incredibly simple machine. Not one he planned to build, just one he imagined. It had a long strip of tape, a reading and writing head, and a small set of simple rules. From that simple thought experiment, Turing proved something astonishing. Given enough time and enough tape, this imaginary machine could perform any calculation that any computer could ever perform. In other words, a single universal machine could, in principle, become every kind of computer. Every laptop, every smartphone, every supercomputer ever built. At their logical foundation, they all follow the same basic idea that Turing described. The only real difference is speed. The electronic body arrived under very different circumstances: war. At Bletchley Park, Alan Turing and his colleagues built electromechanical machines to help break Nazi Germany's Enigma code. Then, by 1944, another machine was operating there. It was called Colossus. It became the world's first programmable electronic computer, built to break an even more complex German code. Historians believe the work of these codebreakers shortened the Second World War and saved countless lives. Remember that detail. From the very beginning, computing and codebreaking were deeply connected. Before this documentary ends, those 2 stories will come together again in an extraordinary way. Then came 1945. In Philadelphia, a machine called ENIAC roared to life. It became the world's first fully electronic general-purpose computer. It weighed around 30 tons. It filled an entire room. Inside were more than 17,000 vacuum tubes. Each vacuum tube acted as an electronic switch. They were fragile, made of glass, and together they consumed enough electricity to power a small neighborhood. ENIAC's first programmers were 6 women. They were mathematicians who had originally worked as human computers, solving calculations by hand. To program ENIAC, they had to physically reconnect cables and switches inside the machine itself. Among them were pioneers such as Jean Jennings Bartik and Betty Snyder Holberton, whose contributions were not fully recognized until decades later. ENIAC could perform about 5,000 additions every second. At the time, newspapers called it a giant brain. Today, the smartphone in your pocket is roughly 1 billion times faster. So how did we go from that enormous room-sized machine to this? One invention changed everything. In December 1947, at Bell Laboratories in New Jersey, 3 physicists, John Bardeen, Walter Brattain, and William Shockley, achieved something extraordinary. They found a way to make a tiny piece of crystal perform the same job as a vacuum tube. It could switch electrical current. It could amplify electrical signals. But unlike a vacuum tube, it needed no glass, no glowing filament, and no moving parts. Instead, it guided tiny particles called electrons through a solid material. They called it the transistor. The invention earned them the Nobel Prize. Today, by sheer numbers, the transistor is the most widely manufactured object in human history. Humanity has built more transistors than there are grains of sand on all the world's beaches, and it is not even close. Then came the next breakthrough. In 1958 and 1959, Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor reached the same remarkable idea independently. Instead of connecting transistors one by one with individual wires, why not build many of them together on a single piece of silicon, along with all of their electrical connections? That invention became the integrated circuit, what we simply call the computer chip. Then, in 1965, an engineer at Fairchild named Gordon Moore noticed something unusual. Year after year, engineers were fitting more and more transistors onto a single chip. The number seemed to double at a remarkably steady pace. At first, roughly every year. Later, the estimate was revised to about every 2 years. Moore predicted that this trend would continue. His prediction became known as Moore's Law. It was never a law of physics. Instead, it became something much more powerful, a goal, a promise, an ambition that inspired entire industries to keep making it come true. And for decades, they did. From just a handful of transistors in the early 1960s, to 2,300 on the first commercial microprocessor in 1971, to tens of billions, and in some cases more than 100 billion transistors on a single chip today. Imagine if cars had improved at the same pace. They would cost less than a coin and travel faster than light. Of course, that comparison falls apart, because nothing else in human history has improved this quickly. That relentless progress is why you carry a supercomputer in your pocket. It is why scientists decoded the human genome, why we landed robots on Mars, and why modern artificial intelligence became possible. But before we can understand why this incredible progress is beginning to slow, and why that slowdown may open the door to something far stranger, we need to look inside the machine itself. What is actually happening inside a computer? Not as a metaphor, not as a simplified story. What is it really doing? Surprisingly, the answer fit to a single word: switches. Chapter 3: What a computer actually is. Forget everything that has ever made computers seem intimidating, because the secret is surprisingly simple. A computer is a machine that flips switches. That is all it does. It flips switches trillions of times every second. Everything else, every game, every movie, every spreadsheet, every website, every photograph, and even this documentary, is ultimately the result of those switches changing between two states over and over again. Over the next few minutes, we're going to see how flipping simple switches can create something that almost looks like thinking. Because once you truly understand what a bit is, you will immediately understand why its quantum cousin is so extraordinary. So let us begin with information itself. Strip away every complicated idea and ask a simple question. What is the smallest possible piece of information? It is the answer to a single yes or no question. Is the light on or off? Is there a hole or not? Heads or tails? In 1948, a brilliant mathematician at Bell Labs named Claude Shannon built an entire mathematical theory around this simple idea. For its basic unit, he used a name that his colleague John Tukey had coined: the binary digit, or more simply, the bit. A bit has only two possible states. We usually write them as 0 and 1. At first, that sounds incredibly limited, but the real power comes when bits work together. One bit gives you two possible values: 2 bits give you 4. 0, 0, 0, 1, 1, 0, and 1, 1. Add a third bit, and the number doubles again to 8. Every time you add one more bit, you double the number of possible combinations. Just 8 bits together, called 1 byte, can represent 256 different combinations. That is enough to assign codes to the letters, numbers, and punctuation marks you use every day. Join together millions or billions of bits, and suddenly you can represent a photograph, a movie, an entire human genome, or even everything stored inside your phone. This system of representing every number using only zeros and ones is called binary. Computers use binary for one very practical reason. 2 clearly different states are easy to build, and they are easy to tell apart. A wire can have electrical voltage, or it can have none. A tiny magnetic region can point one way or the opposite way. Real-world signals are never perfect. Electrical noise can distort them. But when there are only 2 clearly separated choices, even a slightly imperfect one is still easy to recognize as a 1. That is the real strength of binary. It is not clever because it's complicated, it is powerful because it is reliable. Now let us look at the switch itself. The easiest way to understand a transistor is to imagine a valve. Think of a tap controlling the flow of water through a pipe. Now, replace the water with electric current. And instead of turning the tap with your hand, imagine another electrical signal controlling it. When a small electrical voltage is applied to the transistor, it allows current to flow. That represents a 1. Remove that voltage, and the current stops flowing. That represents a 0. In its simplest form, a transistor is electricity controlling electricity, all inside a tiny piece of silicon that is smaller than a virus, and it can switch between these 2 states billions of times every second. But this is where the comparison with a water tap ends. Unlike a tap, nothing inside a transistor physically moves. There are no tiny gears, no valves opening and closing, no friction, no wear. Instead, invisible electric fields guide electrons through the crystal. That is why transistors can be incredibly small, incredibly fast, and astonishingly reliable. Now remember one word: switch, because everything you are about to learn is built on switches that always have a definite answer. They are either on or off, 0 or 1, nothing in between. Later in this documentary, you will meet a very different kind of switch, one that refuses to settle on just one answer. You will also see 2 simple operations that seem as though they should make information more random, yet somehow restore it perfectly, something no ordinary computer built from these switches can ever do. So remember this world of neat, predictable certainty, because we are about to leave it behind. Now the story becomes even more interesting. Suppose you connect 2 switches one after the other. Engineers call this a series connection. In this arrangement, electricity flows only if both switches are turned on. In other words, the circuit performs the logical operation called AND. Now place those same 2 switches side by side. This is called a parallel connection. Now electricity flows if either switch is on. That performs the logical operation called OR. Add one more kind of switch, one that reverses whatever it receives. If the input is 0, the output becomes 1. If the input is 1, the output becomes 0. That is called NOT. These simple building blocks are known as logic gates. They are the basic building blocks of every computer ever made. In 1937, Claude Shannon proved something remarkable. He showed that by combining these simple logic gates in different ways, you could build any logical operation imaginable. Then comes an even bigger surprise. Arithmetic is really just logic wearing a different disguise. Connect a few logic gates in exactly the right pattern, and they can add 2 numbers together, including carrying the extra one, just as you learned in school. Combine many of these adding circuits, and they can add enormous numbers. From addition comes subtraction. From subtraction comes multiplication, then division. And from those foundations come physics simulations, computer graphics, engineering, artificial intelligence, and almost every modern computer program. Now, zoom out. A computer processor, or CPU, is simply an enormous city built from these logic gates. There are billions of them. Some perform arithmetic, some compare numbers, others make decisions. If this value is 1, do this. Otherwise, do something else. Coordinating everything is a timing signal called the clock. Billions of times every second, the clock sends out another pulse. With each pulse, the entire processor updates its state together. Next to the processor sits memory. Think of it as a vast collection of tiny storage locations. Each one holds a single bit, sometimes as a tiny electrical charge, sometimes using another stable electronic arrangement. Every location has its own address, rather like houses on a street or mailboxes in a neighborhood. The processor spends its entire life repeating the same 3 steps, again and again and again. Fetch an instruction, decode what it means, execute it. This design was described in 1945 by the brilliant mathematician John von Neumann. Years earlier, he had also written one of the most important mathematical foundations of quantum measurement. Remember his name. He is the only major figure in this story who helped lay the foundations of both classical computing and quantum computing, long before anyone imagined bringing the two together. So what is software? Surprisingly, software is made of bits too. It is simply another pattern of zeros and ones stored in memory. Some patterns mean add, others mean compare, others mean jump to another instruction. This was Ada Lovelace's great insight. The machine's behavior could itself be stored as information. Instead of rebuilding the machine every time, you simply changed the instructions. The hardware stayed exactly the same, only the software changed. Before we move on, there is one final idea from Claude Shannon. It is one of the most important ideas in this entire documentary. Information is something that can be measured, just like length or weight. And information is always physical. It must exist somewhere, inside a punched hole, an electrical voltage, a magnetic surface, or some other physical object. Information can never exist without a physical form. Keep that idea in mind. Later, a physicist named Rolf Landauer captured it in a simple sentence: information is physical. That single sentence quietly explains almost everything that follows. Because if information must always exist in physical objects, then the laws of physics also determine the ultimate limits of computation. Change the laws of physics, and you change what a computer can do. By the end of the 20th century, this was the complete picture. From ENIAC to the modern internet, every computer followed the same basic design. Information was stored as bits. Every bit was either 0 or 1. Transistors flipped those bits, logic gates processed them. And the path to making computers better seemed obvious. Make the switches smaller, fit more of them onto every chip, and switch them even faster. For more than 50 years, that strategy transformed the world. It became one of the most successful technological advances in human history. Then, quietly, in the early 2000s, engineers inside the semiconductor industry began noticing something unexpected. The switches were approaching a limit, not a limit of money, not a limit of engineering skill, not even a limit of human imagination, a limit set by the laws of nature themselves. Chapter 4, The Wall. Every story of exponential progress eventually ends the same way. Sooner or later, it runs into something that refuses to move. Today, Moore's law is running into not one wall, but 3. The first wall is size. The most advanced transistors built today contain features only a few nanometers across. That is only a few dozen atoms wide. Think about that for a moment. A machine component manufactured by the trillions is now measured in individual atoms. There is only so much smaller you can go. For one simple reason, atoms do not come in smaller sizes. But something even stranger happens before we reach that limit. Inside every transistor are tiny insulating barriers. As those barriers become only a few atoms thick, electrons begin behaving in a way that seems impossible. Instead of going over the barrier, they sometimes appear on the other side. It is almost as if a ghost walked straight through a solid wall. Physicists call this quantum tunneling. For chip designers, it is a nightmare. A switch that is supposed to be completely off begins leaking electricity. Zeros begin behaving a little like ones. And the reliable certainty that computers depend on starts to disappear. Here, the story takes an unexpected turn. The transistor was never completely classical to begin with. It has always depended on the strange rules of quantum physics. Electrons moving through silicon obey quantum mechanics. So do lasers. So do the LED lights illuminating your screen right now. In other words, many of the technologies that transformed the 20th century were already built on quantum physics. Historians sometimes call this the first quantum revolution. Quantum physics was used not to build quantum computers, but to create reliable, everyday technologies that behave in predictable, classical ways. The problem appears only when everything becomes unbelievably small. The individual parts have always followed quantum rules, but as engineers continue shrinking them, those quantum effects become impossible to ignore. Eventually, the strange behavior of the tiny parts begins to overpower the predictable behavior of the whole machine. And that changes the question completely. Instead of trying to hide quantum behavior, what if we used it? Instead of forcing nature to behave like an ordinary switch, what if information itself were stored in quantum states? That idea marks the beginning of what many scientists call the second quantum revolution, and it is even stranger than the first. The second wall is heat. Every time a transistor switches between 0 and 1, it loses a tiny amount of energy. That energy becomes heat. One transistor produces almost none, but billions of transistors switching billions of times every second produce an enormous amount. By around 2005, chip manufacturers reached a difficult limit. They could continue placing more transistors onto each chip, but they could no longer keep making the chips run much faster. Faster clock speeds meant more heat, too much heat. If they pushed much further, the chips would simply become too hot to operate efficiently. That is why if you look closely at modern processors, their clock speeds have changed very little over the past 20 years. Instead of making one processor dramatically faster, engineers began placing multiple processing cores onto a single chip. But beneath that engineering challenge lies something even more fundamental. In 1961, the IBM physicist Rolf Landauer discovered a remarkable principle. Whenever a computer erases a bit of information, for example, changing a 1 back to a 0, there is a minimum amount of energy that must be released. That limit is not caused by poor engineering. It is required by the laws of thermodynamics. Information is physical, and destroying information always produces heat. That means ordinary computers constantly throw information away. Take an AND gate. It receives 2 input bits, but it produces only 1 output bit. Some information disappears in the process. Modern computation, as we know it, is constantly discarding information, and every time it does, a little more heat is produced. Keep that idea in mind. It will become surprisingly important later, because quantum computers are built from a very different kind of logic. Their fundamental operations are designed so that information is never thrown away. But the third wall is the one this documentary is really about, because unlike the first two, no breakthrough in engineering can overcome it. Some problems do not simply become more difficult as they grow, they become overwhelmingly difficult. Their complexity does not increase steadily, it explodes. There is an old legend about the invention of chess. According to the story, an emperor was so delighted with the game that he offered its inventor any reward he wished. The inventor asked for something that sounded almost laughably modest. Place 1 grain of rice on the first square of a chessboard, 2 grains on the second, 4 on the third. Then keep doubling the number for every one of the board's 64 squares. The emperor smiled. It sounded like a bargain, so he agreed. But the numbers grew faster than anyone expected. By the 21st square, the emperor already owed more than 1 million grains. By the 41st square, more than 1 trillion. And by the final square, the total exceeded 18 quintillion grains of rice. That is an 18 followed by 18 zeros. Far more rice than the entire world could produce over many centuries. The emperor was not bad at mathematics. He was simply human, because human intuition is not built to understand exponential growth. Each step feels small, but together they become something enormous. Now meet the kinds of problems that grow exactly like those grains of rice. Imagine a delivery company trying to find the shortest possible route through 60 cities. The question is easy to understand. Even a child can grasp it. But the number of possible routes is almost beyond imagination. It has roughly 80 digits. That is comparable to the estimated number of atoms in the entire observable universe. Checking every possible route is not merely difficult, it is practically impossible. And every additional city makes the problem grow exponentially harder. Smart algorithms can often find very good routes, but for large problems, finding the absolute best answer remains out of reach. Many important real-world problems behave the same way: scheduling, logistics, designing computer chips, predicting how proteins fold, breaking encrypted codes. Then there is another problem, one that nature quietly solves every moment of every day: Chemistry. Every molecule is a quantum object. Its electrons do not sit in neat little positions like beads on a wire. Instead, each electron exists as a spread-out cloud of possibilities. Even more remarkably, those clouds become deeply connected with one another. The state of one electron cannot always be described independently from the others. To predict the exact behavior of a molecule, a classical computer must keep track of all of those connected possibilities at the same time. And the amount of memory needed grows exponentially. Once again, the rice grains return. Every additional particle roughly doubles the amount of information that must be tracked. One published estimate illustrates just how extreme this becomes. To describe the complete quantum state of a single caffeine molecule, the molecule in your morning coffee, with full precision, would require more classical bits than there are atoms in a small planet. Think about that. Every morning, your cup of coffee quietly performs a calculation that no computer on Earth can fully reproduce. Perhaps it deserves a little more respect. Now, to be fair, chemists have developed brilliant approximation methods. For many molecules, those methods work extremely well. And later in this documentary, we will see why they are so valuable. But for some of the most important materials, the approximations begin to fail. The active centers of catalysts, advanced batteries, superconductors, in these cases, the exponential explosion returns, still standing, still undefeated, guarding some of the most valuable scientific knowledge on Earth. Now consider something even more remarkable. Nature solves these supposedly impossible problems constantly, without effort. Every leaf carrying out photosynthesis, every protein folding itself inside your cells in a fraction of a second, every caffeine molecule simply existing inside your coffee. In a very real sense, each is performing the exact quantum behavior that pushes our most powerful supercomputers beyond their limits. Machines that fill entire buildings, machines that consume as much electricity as a small town. Nature is not struggling, only our computers are. That leads to a surprisingly simple question. If nature finds these problems easy, and our computers find them impossible, perhaps the problem is not how powerful our computers are. Perhaps the problem is what kind of computers they are. Every computer humanity has ever built, from Jacquard's loom to the most powerful supercomputer on Earth, belongs to the same family. They are all classical computers. They store definite bits, they use definite switches, and they process one definite configuration at a time. But what if we built a computer from the same strange rules that nature itself uses? A machine whose basic building blocks obey the same laws as the electrons inside that caffeine molecule. In 1981, a Nobel Prize-winning physicist stood before an audience and asked exactly that question. Soon, you will hear his words. But his question was only possible because of a scientific revolution that had begun decades earlier. Perhaps the strangest and most profound revolution in the history of science. It began in Berlin in the year 1900 with a cautious and deeply conservative physicist, a man who believed he was solving nothing more than a small technical problem about light bulbs. Instead, he accidentally changed our understanding of reality forever. Chapter 5. The Reluctant Revolution. Heat almost anything enough and it begins to glow. A campfire glows red, hot steel glows orange, heat it even more and it turns yellow, hotter still and it shines white. By the year 1900, German physicists wanted to understand this familiar phenomenon with complete precision. Part of the reason was practical. Germany's electric lighting industry was expanding rapidly. Scientists wanted to know exactly how much light a hot object should produce at every color. It sounded like an ordinary scientific problem. Instead, it became a crisis. The best physics of the time made an astonishing prediction. According to the equations, every warm object should release an infinite amount of energy at the violet end of the spectrum and beyond. Infinite. If that were true, every fireplace, every candle, every glowing piece of metal would be unimaginably dangerous. Physicists gave this embarrassing failure a memorable name: the ultraviolet catastrophe. The equations were not just slightly wrong, they were spectacularly wrong. And in science, when the best theories fail that completely, it usually means something fundamental is missing. Enter Max Planck. He was 42 years old, highly respected, careful, methodical, and not the kind of scientist who enjoyed revolutionary ideas. Throughout the autumn of 1900, Planck struggled with the problem. Nothing worked, until he tried one last, desperate idea. What if energy was not continuous? What if matter could emit light only in tiny, separate packets? Small bundles of energy instead of a smooth, continuous flow. Each packet would have a specific amount of energy, determined by the color of the light, multiplied by a brand new constant of nature. A number so incredibly small that it's almost impossible to imagine. Planck called these tiny packets quanta. The word comes from Latin and simply means, how much? In December 1900, he presented the idea to the scientific community. Privately, he disliked it. Years later, he described it as an act of desperation. He hoped someone else would eventually explain the problem without needing such a strange assumption. No one ever did. Instead, things became even stranger. In 1905, a 26-year-old patent clerk working in Switzerland took Planck's idea more seriously than Planck himself. His name was Albert Einstein. Einstein applied the idea of energy packets to another mystery, the photoelectric effect. Scientists had noticed something puzzling. Shine light onto certain metals and electrons are knocked free. But the details made no sense. A faint violet light could release electrons immediately. A brilliant red light, no matter how bright, could not release any at all. If light were simply a continuous wave, brightness should have been what mattered. But it wasn't. Einstein proposed a bold explanation. Light itself comes in tiny particles. Today we call them photons. Each photon carries its own packet of energy, and that energy depends entirely on the color of the light. A violet photon carries enough energy to free an electron. A red photon does not. No matter how many red photons arrive together, none of them has enough individual energy to do the job. It was this discovery, not the theory of relativity, that earned Einstein the Nobel Prize. And there's a wonderful irony here. The man who would later become one of quantum theory's greatest critics helped create it. The strange ideas continued to spread. In 1913, a young Danish physicist named Niels Bohr turned them toward the atom itself. Atoms presented another serious problem. According to classical physics, an electron orbiting a nucleus should continuously lose energy. It should spiral inward and crash into the nucleus in a tiny fraction of a second. If that were true, atoms would be unstable. Matter could not exist. Neither could you. There was another mystery. When scientists heated different gases, they did not produce a smooth rainbow of colors. Instead, each element produced a unique pattern of bright lines, almost like its own barcode. No one knew why. Bohr proposed an extraordinary solution. Inside an atom, electrons are allowed to occupy only certain specific energy levels. Imagine the rungs of a ladder. An electron can stand on one rung or another, but never somewhere in between. When an electron drops from a higher rung to a lower one, it releases a photon with exactly the right amount of energy. That energy determines the color of the light. Suddenly, those mysterious barcodes made perfect sense. They were simply the atom's energy ladder, made visible. Bohr's simple model predicted the spectrum of hydrogen with remarkable accuracy, but it also introduced an idea that will become incredibly important later in this documentary. Imagine choosing just two rungs on that ladder. Call the lower one 0. Call the upper one 1. Without realizing it, you have created nature's own version of a bit. Remember that ladder. We're going to return to it. Then in 1924, another remarkable idea appeared. It came from a young French physicist and aristocrat named Louis de Broglie. Einstein had shown that light, which had always been thought of as a wave, could also behave like a particle. De Broglie asked the opposite question. If waves can behave like particles, could particles also behave like waves? Could electrons, atoms, perhaps even all matter have wave-like properties? Within just a few years, experiments gave an astonishing answer. Yes. Scientists watched electrons produce the same kinds of interference patterns as ordinary waves. Matter waves were real. Everything around you has a wavelength, even you. Your wavelength is unimaginably small. That is the only reason you have never noticed yourself behaving like a wave, or diffracting as you walk through a doorway. Now the revolution needed something else. It needed a new mathematics. And what happened next was an extraordinary burst of scientific creativity, one that remains almost unmatched in the history of science. In June 1925, a 23-year-old German physicist named Werner Heisenberg escaped to the small island of Helgoland in the North Sea. He was suffering badly from hay fever, and the island's almost complete lack of pollen offered some relief. There, working in isolation, he made a bold decision. Instead of building a theory around things no one could directly observe, he would build it using only what experiments actually revealed: the colors of light emitted by atoms. Following that idea led him to a completely new kind of mathematics, one where the order of multiplication mattered. In ordinary arithmetic, this multiplied by that gives the same answer as that multiplied by this. But in Heisenberg's new mathematics, the order could change the result. It was something entirely unfamiliar. Later, Heisenberg recalled finishing one of his calculations at around 3 o'clock in the morning. He was so overwhelmed that he could not sleep. He felt as though he had looked beneath the surface of the atomic world and glimpsed something unexpectedly beautiful. As dawn approached at Tart, he climbed a rocky cliff overlooking the sea and watched the sun rise. Modern quantum mechanics was only a few hours old. A few months later, during Christmas of 1925, high in the Swiss Alps, another physicist found a completely different path. His name was Erwin Schrödinger. Instead of focusing on observable quantities, he developed a single elegant equation describing how de Broglie's matter waves change and evolve over time. At first glance, Schrödinger's theory looked nothing like Heisenberg's. They seemed to describe entirely different worlds. But when physicists examined them more closely, they discovered something astonishing. The two theories were mathematically equivalent, two completely different roads leading to the same destination. Within another 2 years, a quiet English physicist named Paul Dirac unified both approaches into an even deeper mathematical framework. And then something remarkable happened. The equations predicted the existence of an entirely new kind of particle, a particle with the same mass as an electron, but the opposite electric charge, antimatter. No one had gone looking for it. The mathematics predicted it first, and in 1932, experiments confirmed that it was real. Even today, some form of Schrödinger's wave equation remains at the heart of quantum mechanics. Every quantum computer ever built relies on it. But this raises an obvious question. If matter behaves like a wave, what exactly is waving? The answer arrived in 1926 from the German physicist Max Born, and this is where quantum theory becomes truly strange. So let us take it slowly. Born proposed that the quantum wave is not a wave of matter. Instead, it is a wave of possibility. At every point in space, the wave has a value called its amplitude. That amplitude is not the particle itself, but if you square its value, you obtain the probability of finding the particle there when you make a measurement. That may sound like a small mathematical detail. It is not. It changes everything. Before you make a measurement, the electron does not secretly have one fixed position that you simply do not know. According to quantum mechanics, the spread-out cloud of possibilities is the complete description of reality. Then, when you make a measurement, all of those possibilities disappear. Only one outcome remains. Which outcome appears is fundamentally random. Not random because we lack information. Not like flipping a coin, where in principle perfect knowledge could predict the result. This randomness is different. It has no deeper hidden cause, as far as more than a century of increasingly precise experiments has been able to show. Then in 1927, Werner Heisenberg introduced another revolutionary idea, the uncertainty principle. Some pairs of physical properties, such as a particle's position and its momentum, cannot both be known with perfect precision at the same time. This is not because our measuring instruments are imperfect. It is not because scientists are careless. According to quantum mechanics, nature itself does not assign perfectly precise values to both properties simultaneously. The more precisely one becomes defined, the less precisely the other can be. Reality itself has built-in limits. Later that same year, many of the greatest physicists in the world gathered in Brussels for the Solvay conference. The famous group photograph from that meeting has become one of the most remarkable images in scientific history. Of the 29 people in the picture, 17 either had already won or would later win the Nobel Prize. It was there that one of history's greatest scientific debates truly began. Einstein could not accept a universe governed by fundamental randomness. In a letter to Max Born, he famously wrote, "God does not play dice." According to the well-known story, Niels Bohr eventually grew tired of hearing the argument. He replied that Einstein should stop telling God what to do. Day after day, Einstein arrived with brilliant thought experiments designed to expose a contradiction in quantum theory. And day after day, Bohr found the weakness in each argument. Those who witnessed the debates believed Einstein lost every round, yet he never admitted defeat. He did not argue that quantum mechanics failed. The theory clearly worked. Instead, he believed it could not be the complete story. To him, it was like looking at a blurry photograph. Useful, but hiding a sharper reality underneath. Einstein continued thinking about that problem for another 8 years. Then, in 1935, he launched the most famous challenge of his career, a thought experiment so deep and so subtle that physicists needed more than 30 years to fully understand its consequences. And in one of the greatest ironies in the history of science, that very challenge would eventually become one of the foundations of the quantum computers this documentary is about. Chapter 6, The Argument That Wouldn't Die. In May 1935, Albert Einstein, now living at Princeton University after fleeing Nazi Germany, published a scientific paper with two younger colleagues, Boris Podolsky and Nathan Rosen. Today, physicists simply call it the EPR paper. Its purpose was straightforward: challenge the strangest prediction of quantum mechanics. According to quantum theory, two particles can interact and then become linked in an extraordinary way. Afterward, they no longer behave as two completely separate objects. Instead, they share a single quantum state. Individually, neither particle has completely definite properties, yet somehow their properties remain perfectly connected. Measure one particle and you immediately know something about the other, even if it is on the opposite side of the galaxy. Later that same year, Erwin Schrödinger gave this remarkable phenomenon its name: entanglement. He believed it was not just another strange feature of quantum mechanics. He called it the defining feature, the one that separates the quantum world from everything our everyday intuition expects. Einstein was deeply uncomfortable with this idea. His objection was simple: take quantum mechanics literally. Before either particle is measured, neither has a definite value. Yet the instant one particle is measured, the other somehow behaves as though its own value has also been determined, no matter how far apart the two particles are. Einstein believed only two explanations seemed possible. Either some influence was traveling faster than light, or the theory was incomplete. Perhaps the particles had secretly carried matching instructions from the very beginning, like two sealed envelopes, prepared in advance and opened only later. Years afterward, Einstein famously described the alternative as spooky action at a distance. To common sense, the sealed envelope sounded far more reasonable. That same remarkable year, Erwin Schrödinger introduced another famous thought experiment, one that almost everyone has heard of: Schrödinger's cat. Imagine a cat inside a sealed box. Alongside it is a vial of poison. Whether the poison is released depends on a single quantum event. According to a literal reading of quantum mechanics, until someone opens the box, the cat is described as both alive and dead at the same time. Today, many people think Schrödinger invented the cat to celebrate how strange quantum mechanics is. In reality, he meant exactly the opposite. The cat was a criticism, a protest. Schrödinger wanted to show that if quantum uncertainty spread into the everyday world, it appeared to produce absurd conclusions. His question was simple: where does the quantum world end and the familiar world begin? Nearly a century later, that question remains one of the deepest mysteries in physics. And as we will soon discover, it is also one of the greatest engineering challenges facing everyone trying to build a quantum computer. For the next 30 years, the EPR argument remained unresolved. Most physicists treated it as philosophy. Interesting, perhaps, but impossible to test. So they moved on. They used quantum mechanics, built lasers, built transistors, made remarkable discoveries, while quietly setting aside the uncomfortable question: what is actually real? Then, in 1964, everything changed. A quiet physicist from Northern Ireland named John Stuart Bell found a way to transform philosophy into mathematics. Bell worked at CERN, helping design particle accelerators. Quantum foundations were simply a personal fascination, a hobby. Yet it was Bell who made one of the most important breakthroughs in modern physics. He imagined performing repeated measurements on pairs of entangled particles. Each measuring station would independently choose at the very last moment which property to measure. Then Bell proved something extraordinary. Suppose Einstein was right. Suppose each particle carried a complete set of hidden instructions from the moment they separated. And suppose no influence could travel faster than light. Under those assumptions, there is a strict mathematical limit to how strongly the measurement results can be correlated, a limit that no hidden instruction can ever exceed. But quantum mechanics predicts something different. It predicts correlations that go beyond Bell's limit. This was no longer philosophy. It was a prediction, one that could be tested experimentally. Imagine a game show. Two contestants are placed in separate rooms. They cannot communicate. Each is asked one of several possible questions chosen at random. They win if their answers match in a particular pattern. Bell proved that no strategy prepared in advance, no script, no notebook, no secret plan, could win more often than a certain limit. Yet particles connected through quantum entanglement consistently do better, which leaves only one conclusion. There is no hidden script. For the first time, one of the deepest questions about reality had become an experiment. Now all that remained was to perform it. In 1972, John Clauser and Stuart Friedman, working at Berkeley, carried out the first experimental test using entangled photons. Clauser later admitted something surprising. He expected and even hoped that Einstein would be proven right. Senior physicists warned him not to waste his career. Some dismissed the experiment as philosophy pretending to be physics, but Clauser went ahead anyway. The result? Quantum mechanics was correct. Then, in 1982, Alain Aspect in Paris improved the experiment. He changed the measurement settings while the photons were already traveling, too quickly for any hidden signal to coordinate their answers. Once again, quantum mechanics was correct. Over the following decades, Anton Zeilinger and many other researchers pushed the experiments even further. They tested entanglement across kilometers, between islands, using photons, atoms, and even tiny crystals. Then, in 2015, 3 independent research teams closed all of the major remaining loopholes at the same time. Again, quantum mechanics was right, again and again and again. Sadly, John Bell never lived to see the final verdict. He died unexpectedly in 1990. Reports suggest he was even being considered for the Nobel Prize that same year. But the Nobel Prize is never awarded after death. When the prize finally came in 2022, it went to John Clauser, Alain Aspect, and Anton Zeilinger. Everyone, except the man whose theorem made it all possible. Pause for a moment and consider what those experiments actually tell us. It is one of the deepest discoveries humanity has ever made. Einstein's hidden envelopes do not exist. Entangled particles do not carry pre-written answers waiting to be revealed. And yet, their measurement results remain connected in ways that no classical explanation can reproduce. Reality itself behaves differently from anything our everyday intuition prepares us for. Before measurement, nature genuinely keeps multiple possibilities open, and entanglement links distant particles together in a way that has no ordinary classical equivalent. There are 2 important points we should not forget. First, none of this allows faster-than-light communication. Each measurement, viewed on its own, still looks completely random, like a series of coin flips. The remarkable pattern appears only when scientists later compare the results using ordinary communication, whether by email, telephone, or any other method that still obeys the speed of light. The universe is astonishingly strange, but it never breaks Einstein's speed limit. Second, Einstein was wrong about entanglement, but that takes nothing away from his greatness. His insistence on asking difficult questions forced physicists to investigate the problem with extraordinary precision. Without Einstein's challenge, entanglement might have remained nothing more than an interesting curiosity. Instead, it became one of the most carefully tested phenomena in all of science. Sometimes, being brilliantly wrong moves science forward just as much as being right. Now remember one word: usable. Because Bell's theorem quietly proved something extraordinary. Entanglement is not just a strange feature of nature, it is a resource a resource that no classical computer can imitate. For decades, that idea remained little more than a philosophical curiosity. Then a new generation of physicists asked a different question. Not, is entanglement real? But, what can we do with it? The answer begins by rebuilding the smallest building block of every computer ever made, the humble bit. Except this time, it is going to become quantum. Chapter 7, the qubit. A classical bit, as you now know, is simply a physical yes or no answer. A voltage is present or it is not. A hole is punched or it is not. A switch is on or off. Every bit has one definite value, always. A quantum bit or qubit is very different. A qubit is also built around a yes or no question. But this time the question is asked of a quantum object. And as we have just discovered, quantum objects do not always have definite answers until they are measured. A qubit can be created in several different ways. It might use an electron's spin, a tiny magnetic property that can point up or down. It might use a photon whose polarization is horizontal or vertical. Or, most commonly today, it uses an atom, or an atom-like electrical circuit, occupying one of two possible energy levels. Think back to Bohr's energy ladder. The lower rung becomes 0, the next rung becomes 1. Exactly as promised, nature provides its own version of a bit. But now comes the extraordinary part. Because a qubit is a quantum object, it does not have to remain on just one rung. Instead, it can exist in what physicists call a superposition, a genuine combination of 0 and 1 at the same time. This idea is often explained poorly, so let us slow down and build it carefully. A superposition is described using two numbers. One is associated with 0, the other is associated with 1. These numbers are called amplitudes, the same amplitudes we first encountered when Max Born explained the quantum wave. If you square an amplitude, you obtain the probability of measuring that particular outcome. So a qubit might have a 70% probability of becoming 0 and a 30% probability of becoming 1, or perhaps 50% for each, or almost any other combination. Why no? If that were the whole story, a qubit would simply be a very sophisticated weighted coin. Interesting, perhaps, but not revolutionary. Fortunately, that is not the whole story. Something important is still missing, and that missing piece becomes the driving force behind everything that follows. Unlike ordinary probabilities, amplitudes have something extra. They have direction. Physicists call this phase. You can think of phase as something like the direction of the hand on a clock. An amplitude can point one way or the opposite way, or anywhere in between. This single idea changes everything. Ordinary probabilities can only be added together, but amplitudes can do something probabilities never can. They can cancel each other out. Imagine two different paths leading to the same wrong answer. If one path carries an amplitude pointing in one direction, and the other carries an amplitude pointing in exactly the opposite direction, the two cancel. The wrong answer simply disappears. Its probability becomes 0. Keep that idea firmly in your mind. It may seem abstract right now, but in the next chapter, it becomes the key that unlocks quantum computation. And a few chapters from now, you will actually see simple quantum gates demonstrating that these hidden amplitudes are real, for now. Let us talk about the analogy almost everyone uses. You have probably heard people say that a qubit is like a spinning coin. While the coin is spinning, it is neither clearly heads nor clearly tails until it lands. As a first mental picture, that analogy is helpful, but it also hides two extremely important differences. First, a spinning coin is actually either heads or tails at every instant. You simply do not know which. Its uncertainty comes from your lack of information. A qubit is different. As Bell's theorem and decades of experiments have shown, there is no hidden answer waiting to be discovered. The superposition itself is the physical reality. Second, a spinning coin has no phase. No matter how many spinning coins you combine, they can never cancel one another. Quantum amplitudes can, and that ability to interfere, to reinforce some outcomes while eliminating others, is exactly what gives quantum computers their extraordinary power. There's a beautiful way to picture a single qubit honestly. In fact, it has become one of the unofficial symbols of quantum computing. It is called the Bloch sphere, named after the physicist Felix Bloch. Imagine a globe. The North Pole represents 0, The south pole represents 1. Now imagine that every point on the surface of that globe represents a different, perfectly valid qubit state. The closer you are to the north pole, the more likely the qubit is to become 0 when measured. The closer you are to the south pole, the more likely it is to become 1. Around the equator, both outcomes are equally likely. The position around the globe, the longitude, represents something else. The qubit's phase, that hidden direction we discussed earlier. You cannot see the phase from a single measurement, but it becomes critically important when quantum states begin to interfere with one another. A classical bit gives you only 2 possible states. A qubit gives you an entire globe of possibilities. There is one important detail to remember. The Bloch sphere describes only a single qubit. Once you have 2 qubits, or 10 or hundreds, the picture no longer fits inside ordinary 3-dimensional space. The mathematics still works perfectly, but even physicists can no longer visualize it. At that point, they trust the equations. Then comes something every quantum computer must face: measurement. And measurement comes at a price. Ask a qubit a simple question. Are you 0 or 1? It gives you one ordinary answer, either 0 or 1. Which answer appears is random, with probabilities determined by the amplitudes we discussed earlier. That is all you receive. The rich quantum state disappears. The point on the Bloch sphere collapses to one of the poles. The superposition is gone. The phase is gone. The entire landscape of possibilities is gone, irreversibly. If you prepare 1,000 identical qubits and measure them one by one, their overall statistics reveal the quantum state you created. But each individual measurement tells you only one answer, and once that measurement happens, there is no going back. As far as every experiment has shown, this is not a limitation of our technology, it is simply how nature works. Now let us scale things up. This is where quantum computing becomes both astonishing and surprisingly difficult. Describing a single qubit requires 2 amplitudes. 2 qubits require 4 amplitudes. 1 for 0, 0, 1 for 0, 1, 1 for 1, 0, and 1 for 1, 1, all existing together. 3 qubits require 8 amplitudes. Every additional qubit doubles the total. Once again, the chessboard returns. The rice grains are back, except this time, the exponential growth is working in our favor. With 50 qubits, the quantum state already requires more than 1 quadrillion amplitudes to describe. With around 300 qubits, the number of amplitudes becomes larger than the estimated number of atoms in the observable universe. Think about that for a moment. A small collection of quantum objects sitting on a laboratory table can require a mathematical description larger than the visible universe itself. This is not science fiction. It is a direct consequence of quantum mechanics. And it is exactly why simulating molecules like caffeine overwhelms even our most powerful classical computers. A classical computer has to keep track of every one of those amplitudes individually. Now comes one of the biggest misconceptions about quantum computing. You will hear it repeated almost everywhere. People often say, a quantum computer tries every possible answer at the same time. That is not true. As in, the quantum amplitudes do evolve together, and that enormous mathematical state is very real, but you can never read all of it. The moment you measure 300 qubits, you receive only 300 ordinary bits, one single result. Chosen according to the probabilities, everything else disappears. Imagine owning a library larger than the universe, but being allowed to read only one sentence, chosen at random, before the entire library vanishes forever. That is the challenge every quantum algorithm must overcome. And that is the true art of quantum computing. The goal is not to calculate every answer and read them all. That is impossible. Instead, the goal is to carefully guide those hidden amplitudes to make the wrong answers cancel one another through interference, while the right answer grows stronger and stronger. Then, when the final measurement happens, the answer you want is the one most likely to appear. In other words, you do not beat the lottery by buying every ticket. You reshape the odds before the drawing ever begins. One small historical note before we continue. The word qubit was introduced in the 1990s by physicist Benjamin Schumacher. He has said it began as a simple play on words, a surprisingly light-hearted name for one of the most profound ideas in modern information science. But one question still remains. How do those hidden amplitudes actually interfere? How do they cancel some possibilities while strengthening others? The answer was first revealed more than 2 centuries ago, using nothing more than a candle, a screen, and 2 narrow slits. An experiment many physicists still describe as the most beautiful in all of science. Chapter 8: Interference, the Engine. In 1801, the English scientist Thomas Young carried out a beautifully simple experiment. He cut 2 narrow slits into a screen. Then he shone light through them and looked at the wall behind. If light were made only of tiny particles, he expected to see 2 bright bands, one behind each slit. Instead, he saw something completely different. A repeating pattern of bright and dark stripes. Bright, dark, gradually fading toward the edges. The explanation is surprisingly simple. If light behaves like a wave, then waves passing through the 2 slits spread out and overlap. Where the crests of 2 waves meet, they reinforce each other. The light becomes brighter, but where the crest of one wave meets the trough of another, they cancel. The light disappears. This is called interference. 2 waves combining to produce either more light or none at all. In fact, you may be using the same idea every day. Noise-canceling headphones work by creating a second sound wave that is perfectly out of step with the unwanted noise around you. The 2 sound waves interfere, and much of the noise disappears. That is interference in action. And in 1801, it convinced scientists that light behaves like a wave. But by now, we know something Young did not. As we discovered earlier through the work of Max Planck and Albert Einstein, light also behaves like a particle. That leads to an extraordinary question. What happens if you send those particles through the 2 slits, one at a time? Physicists eventually performed exactly that experiment. One of the most famous versions was carried out in 1989 by Akira Tonomura and his team. Instead of using light, they used electrons. They fired them so slowly that each electron struck the detector and disappeared before the next one was even released. Each electron arrived as a single tiny dot, exactly what you would expect from a particle. But something remarkable happened. As thousands, then millions, of individual electrons accumulated, a familiar pattern slowly emerged. Bright bands, where many electrons landed. Dark bands, where almost none ever appeared. Think carefully about what that means. Each electron traveled alone. There were no other electrons nearby. Nothing else was available to interfere with. And yet, their overall pattern still showed interference. The unavoidable conclusion is astonishing. Each electron's wave of possibility, its quantum amplitudes, passed through both slits. Those amplitudes interfered with one another before the electron finally appeared as a single dot. It was not the electron itself exploring 2 paths, it was its quantum possibilities. This experiment has often been called the most beautiful experiment in all of physics, and it captures the essence of quantum mechanics in a single image. Every individual result appears random, yet together they form a pattern of perfect order. Then comes one final surprise. Place a detector beside the slits. Simply ask which slit each electron passes through. The interference pattern disappears. Immediately, the beautiful stripes vanish. Only the 2 ordinary particle bands remain. The moment you extract information about the electron's path, the superposition is destroyed. The amplitudes can no longer interfere. They can no longer cancel one another. Measurement has already forced the electron to choose. This is exactly what we encountered in the previous chapter. Measurement changes the quantum state. In the quantum world, observation is never completely passive. To measure is to interact. In that sense, looking is also touching. Electrons behave differently when they are being observed. In that respect, they are strangely like us. Now we reach one of the most important ideas in this entire documentary, because this is the basic principle behind every quantum algorithm ever created. Imagine quantum computation as an enormous network of carefully designed double-slit experiments. The first step is superposition. The qubits create an enormous collection of possible computational paths. Each possible answer follows its own path, and each path carries its own quantum amplitude, complete with its own phase. Then comes the real genius. The algorithm carefully changes those phases. Each path is rotated by just the right amount, according to the mathematical structure of the problem being solved. This is where the computation truly happens. If the algorithm is designed correctly, something extraordinary occurs. The amplitudes leading to wrong answers begin canceling one another, just like the dark stripes in Young's experiment. Meanwhile, the amplitudes leading toward the correct answer reinforce one another, growing larger and larger like the bright stripes. Only then does the final step happen: measurement. Now the probabilities have been reshaped. The correct answer has become far more likely to appear. The lottery has not been eliminated, but the odds have been carefully engineered in your favor. That is what a quantum computer really does. Superposition creates many possible computational paths. Interference strengthens some and removes others. Measurement produces one final answer. A quantum computer does not every possible answer and then choose the best one. Instead, it carefully arranges for the wrong answers to cancel themselves out. That is the true power of quantum computation. And it is also why building useful quantum algorithms is so difficult. Not every problem has the hidden mathematical structure needed for this kind of interference. Only certain problems contain the right patterns, the right symmetries, the right relationships that allow amplitudes to be choreographed in this way. Remember that. It explains both why quantum computers may one day break certain kinds of encryption and why they will never make every computer task dramatically faster. Before we continue, there is one important question. What is an electron actually doing between the slits and the screen? The honest answer is, physicists still disagree. Different interpretations of quantum mechanics tell different stories. The Copenhagen interpretation associated with Niels Bohr treats the wave as a mathematical tool for predicting measurement outcomes. It argues that asking what the electron is really doing before measurement simply has no meaningful answer. The many worlds interpretation offers a very different picture. According to it, the wave never truly collapses. Instead, every possible outcome occurs, each within its own branching reality. Other interpretations, including pilot wave theory and objective collapse theories, offer different explanations still. Here is the important point. So far, every one of these interpretations makes exactly the same experimental predictions. The mathematics has been tested with extraordinary precision, yet the deeper reality behind it remains one of the greatest open questions in science. Quantum computers work under every one of these interpretations, which is why the physicist Richard Feynman could famously say that nobody truly understands quantum mechanics. And perhaps the remarkable thing is this: you do not have to completely understand it to build technology that uses it. Now we have the engine, interference. But every engine needs fuel. And the fuel of quantum computing is the very phenomenon that Einstein once dismissed as spooky. It is time to look directly at entanglement, not as a paradox this time, but as a resource. Chapter 9, Entanglement, the fuel. Take two qubits, bring them close together, let them interact in exactly the right way. Something remarkable happens, something with no classical equivalent. The two qubits stop behaving as separate objects. They no longer have independent quantum states. Ask the mathematics, what is the state of qubit A? Surprisingly, there is no complete answer. The only complete description belongs to both qubits together. It is as though the two have become a single quantum system. Here's a helpful picture. Imagine two ordinary coins. Now imagine they somehow melt together into one extraordinary supercoin. That supercoin exists in a blend of both heads and both tails at the same time. Now separate the two coins and send them to opposite sides of the Earth. When each coin is flipped, its result looks completely random. Heads, tails, heads, tails. But compare the two records afterward, and they match again and again and again. Not because one coin somehow told the other what to do, but because, at the deepest level, they were never truly separate. They were always parts of one larger quantum state. Like every analogy in this documentary, this one has its limits. Matching results alone would not be mysterious. Two envelopes containing the same pre-written letter would also match. And that was exactly Einstein's explanation. He believed the particles carried hidden instructions from the very beginning. But Bell's theorem showed something remarkable, and decades of experiments confirmed it. Entangled particles agree and disagree across many different kinds of measurements in ways that no hidden script can ever reproduce. The correlations are real, the hidden instructions are not. That combination perfect coordination without pre-written answers, exists nowhere in classical physics. Erwin Schrödinger was right. Entanglement is not just another feature of quantum mechanics, it is its defining feature. So, how do you create entanglement? There are several ways. For example, shine a laser into certain specially prepared crystals, and occasionally, one photon splits into two entangled photons. Experiments have used this method for decades. Inside a quantum computer, entanglement is created much more deliberately. Quantum gates are used to make one qubit's behavior depend directly on another. The process itself is not especially mysterious. The meaning of what it creates is. Now let us look at the three most important rules of entanglement. These rules support almost everything that comes later. First, entanglement cannot be used to send messages faster than light. This is one of the most important results in quantum physics. Each qubit, viewed by itself, looks completely random. Only when two observers later compare their results, using ordinary communication, do the hidden correlations appear. No instant messaging, no faster-than-light communication. Not because our technology is limited, because nature itself forbids it. Quantum mechanics and Einstein's theory of relativity remain perfectly compatible. Second, quantum information cannot be copied. In 1982, physicists William Wooters, Wojciech Zurek, and independently Dennis Deeks proved what is now called the no-cloning theorem. It says something surprisingly simple. There is no physical process that can make a perfect copy of an unknown quantum state. None. This fact reaches into every corner of quantum computing. A quantum computer has no copy and paste, no backup file, no save button. Every calculation must protect the original quantum information from beginning to end. Later, this rule will make quantum error correction seem almost impossible, but the same rule also becomes one of quantum physics' greatest gifts. If the quantum state cannot be copied, then it also cannot be secretly intercepted without changing it. Anyone attempting to read it inevitably leaves evidence behind. Nature itself provides the tamper seal. Entire systems for ultra-secure quantum communication are built on this single idea. Third, maximum entanglement is exclusive. Physicists sometimes describe this by saying entanglement is monogamous. If two qubits are perfectly entangled with each other, they cannot also be perfectly entangled with anything else. There is no room for a third partner. That simple rule turns out to be incredibly useful. It helps guarantee the security of quantum communication. An eavesdropper cannot secretly share a perfectly entangled connection. There simply is no space left. So, what is entanglement actually for? Inside a quantum computer, it performs one essential task. It binds many individual qubits into one enormous quantum system. Without entanglement, 50 qubits are simply 50 independent quantum objects. Useful, but still limited. In fact, such systems can often be simulated efficiently on ordinary classical computers. With entanglement, everything changes. Those separate qubits become one shared quantum state. The enormous mathematical object we explored in the previous chapter, the one whose description can require more numbers than there are atoms in the observable universe. That is where quantum computing gains its extraordinary potential. Entanglement creates the space where quantum advantage can exist. And entanglement is valuable for another reason. It is not only useful inside a quantum computer, it can also be used between quantum computers. Scientists can spend entanglement almost like a resource. It can teleport quantum states, connect distant quantum processors, and distribute encryption keys with extraordinary security. Later in this documentary, we will see all of these ideas in action. Now step back for a moment and look at what more than a century of physics has given us. Superposition, a qubit that can exist in many possible states. Interference, a way to strengthen correct answers while eliminating the wrong ones. Entanglement, a resource that joins many qubits into one unified quantum system in ways no classical physics can imitate. And measurement, the unavoidable final step where all that rich quantum information becomes a single answer. For decades, these ideas fascinated physicists. They filled research papers, they sparked arguments, they inspired philosophy, but they seemed to have little practical use. Then, in May 1981, at a conference just outside Boston, a 62-year-old Nobel Prize winner walked onto the stage. He loved playing the bongo drums. He hated vague thinking. And before his talk was over, He would challenge the scientific world with an idea that helped launch the quantum computing revolution. Chapter 10. Nature isn't classical, damn it. In May 1981, a small conference took place at MIT's Endicott House, just outside Boston. It was called the Physics of Computation. The gathering was unusual. Only about 50 people attended. Some were computer scientists fascinated by physics. Others were physicists fascinated by computation. Very few people in the world cared deeply about both. One of the organizers was Rolf Landauer of IBM, the same scientist whose work taught us that information is physical. He would also become one of the field's most thoughtful skeptics. There is another story from that conference. According to long-standing accounts, the keynote speaker, Richard Feynman, agreed to attend only if he was allowed to give a talk. Whether every detail of that story is true or not, one thing certainly is. The group photograph from that meeting captured many of the people who would shape quantum computing over the next 2 decades. None of them knew it at the time. 1 year earlier, a quiet physicist named Paul Benioff had already laid the first real foundation. He showed that a computer built from quantum systems was not just science fiction. It was allowed by the laws of physics. His work proved that quantum objects could perform ordinary computation without violating quantum mechanics. In other words, the answer to an important question had become clear. Could a quantum computer exist at all? Yes. Benioff had shown that it could. His contribution deserves far more recognition than it usually receives. He was also there at Endicott House, presenting his ideas to the small audience. But it was the keynote speaker who changed history. Richard Feynman, Nobel Prize winner, veteran of the Manhattan Project, bongo drummer, safecracker, and one of the greatest physical thinkers of the 20th century. He stood before the audience and asked an astonishingly simple question. Can an ordinary computer simulate nature perfectly? Not approximately, not well enough, exactly. As we discovered earlier, the answer is no. Every additional quantum particle doubles the amount of information needed to describe the system. Very quickly. The mathematics explodes beyond anything a classical computer can handle. Not because engineers lack imagination, not because today's computers are too slow, but because the numbers themselves grow exponentially. Then, Feynman delivered the sentence that has become legendary. A sentence preserved in the published conference proceedings. He said, "Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical." Then he added, "And by golly, it's a wonderful problem because it doesn't look so easy." That was the challenge. Stop fighting quantum mechanics. Start using it. Instead of forcing an ordinary computer to imitate nature, build a computer that follows nature's own rules. If you wanted to simulate molecules, build a machine that speaks the same language molecules do. It was a simple idea, and a revolutionary one. But the field still needed something more. It needed a universal theory. That arrived in 1985. This time from an Oxford physicist named David Deutsch. Deutsch showed that there could exist a universal quantum computer, a single quantum machine capable, in principle, of performing any computation allowed by quantum mechanics. Just as Alan Turing had shown that one universal classical computer could perform any classical computation, Deutsch extended the idea into the quantum world. It was, in many ways, Turing's theorem, rewritten for the actual laws of nature. One historical detail is worth mentioning. Deutsch was deeply influenced by the many worlds interpretation of quantum mechanics. He believed quantum computing offered a way to take that interpretation seriously. Many physicists disagree with his interpretation, but they agree completely with his mathematics. The theorem stands, regardless of how you interpret quantum mechanics. Deutsch also introduced something much smaller, yet historically just as important: the very first quantum algorithm. The problem itself was almost trivial. Imagine trying to determine whether a mysterious coin is ordinary or double-sided when every observation is expensive. A classical method requires 2 observations. Deutsch showed that a quantum circuit could solve the problem with only 1. It was not a practically useful algorithm, but that was never the point. Its importance was far deeper. For the first time, a quantum computer had been shown to perform a task using fewer steps than any classical computer possibly could. The first crack had appeared in a wall that had stood for centuries. Then, in 1992, Deutsch and Richard Jozsa pushed the idea further. They designed another problem, again, highly artificial, again, not something anyone actually needed to solve. But this time, the difference between classical and quantum computation became exponentially larger. Some people dismissed these early algorithms because they solved unrealistic problems. But that criticism misses the point. Think about the Wright brothers. Their first airplane flew only about 120 feet. Nobody wanted an airplane that could travel 120 feet. The important question was whether flight itself was possible. Once that answer became yes, everything else followed. The same was true here. These early quantum algorithms proved that quantum advantage was real. The distance did not matter. The principle did. During the early 1990s, more breakthroughs followed. Bernstein and Vazirani developed new quantum algorithms. Then, in 1994, Daniel Simon introduced another. His problem was still artificial, but it demonstrated a dramatic separation between what quantum and classical computers could do. At first, many reviewers rejected Simon's paper, but one person read it very carefully, a mathematician working at Bell Labs. As he studied Simon's idea, he noticed something remarkable. The algorithm uncovered hidden repeating patterns using interference, and those patterns reminded him of something else, something deeply familiar. The mathematics protecting the world's encrypted secrets. That realization would soon transform quantum computing forever. We will watch that story unfold in Chapter 12. But first, we need to understand the language quantum computers actually speak. Just as ordinary computers rely on logic gates, quantum computers rely on quantum gates, and it is inside those gates that all of the strange ideas we have learned finally become useful. Chapter 11, The Grammar of the Impossible. Think back to the classical logic gates we explored earlier, and or not. These simple arrangements of switches are the building blocks of every classical computer, but there is something important we skipped over. Take an AND gate. It accepts 2 input bits and produces 1 output bit. Some information disappears along the way. If the output is 0, you cannot work backward and know exactly what the original inputs were. Several different inputs could have produced the same result. In other words, an AND gate destroys information. Classical computers do this constantly, and as we learned from Landauer's principle, destroying information always has an energy cost. Some of that energy becomes heat. That is why, at the deepest level, classical computation is irreversible. Once information is thrown away, it is gone. Quantum computing is different. In fact, it cannot work that way at all. The mathematics of quantum mechanics allows only operations that can be completely reversed. Every quantum gate can run backward. Nothing is permanently lost. Nothing is erased. Picture the block sphere again, the globe that represents every possible state of a single qubit. A quantum gate does not crush the globe. It does not tear pieces away. Instead, it simply rotates it around one axis or another, by one angle or another. Every quantum program is nothing more than a carefully choreographed sequence of these rotations. One important clarification: this does not mean quantum computers consume no energy. They certainly do. Their refrigeration systems alone require enormous amounts of power. But the logic itself is fundamentally reversible, and that makes it very different from classical logic. Now let us meet the core vocabulary of quantum computing. Just 4 gates are enough to understand the basic language used throughout the field. The first is the X gate. Think of it as the quantum version of not. It flips 0 into 1 and 1 into 0. If the qubit is in a superposition, the gate simply swaps the 2 parts. So far, everything feels comfortably familiar. It will not stay that way for long. Next comes the Z gate, and this gate has no classical equivalent. The Z gate does not change the probabilities you would measure. Instead, it changes something much more subtle. It changes the qubit's phase. Remember the hidden direction carried by every amplitude, the invisible property that allows interference to happen. The Z gate reverses the phase of the one component while leaving everything else unchanged. If you measure the qubit immediately afterward, nothing appears different. The probabilities are exactly the same. The measurement statistics are exactly the same. From the outside, it looks as though nothing happened. But internally, everything has changed. Because interference depends entirely on phase. The Z gate quietly controls one of the most powerful features of quantum mechanics. It changes what you cannot immediately see, and in doing so, changes what may happen later. Few objects capture the spirit of quantum computing better than this gate. Now we arrive at one of the most important gates of all, the Hadamard gate, usually written simply as H. The Hadamard gate creates superposition. Feed it a definite 0, and it produces a perfectly balanced combination of 0 and 1. On the Bloch sphere, it rotates the state from the North Pole down to the equator. This is the gate that opens new computational paths, and it hides one of the most beautiful demonstrations in quantum computing. Watch carefully. Start with 0, apply a Hadamard gate. Now the qubit becomes an equal superposition. Next, apply another Hadamard gate. At first glance, you might expect the result to remain random. After all, you are acting on something that is already 50-50, but that is not what happens. The final result is 0. Every single time. Not almost every time, every time. Why? Because the second Hadamard gate creates new paths, and those paths interfere. The paths leading to the wrong answer cancel each other completely. Their phases point in opposite directions. The paths leading to the correct answer reinforce one another. It is exactly the same interference pattern we saw in the double-slit experiment. Only now, the entire experiment is happening inside a quantum circuit. This is the demonstration we promised several chapters ago. The hidden phases are real. They produce measurable consequences. And this simple sequence of 2 Hadamard gates is performed routinely millions of times on real quantum hardware. Now let us move beyond a single qubit. The 4th gate is called the C0 gate, short for controlled not. It acts on 2 qubits. Its rule is simple. If the first qubit is 1, flip the second. If the first qubit is 0, leave the second unchanged. It is simply an if-then instruction made physical. Now imagine that the first qubit is not definitely 0 or 1. Instead, it is in a superposition. The C0 gate cannot choose a single action. Quantum mechanics does not allow it to, so something extraordinary happens. The 2 qubits become linked. The output is no longer 2 separate quantum states. It becomes one shared quantum state. The C0 gate creates entanglement. Every entangled pair inside every modern quantum computer begins with gates like this one. Einstein's so-called spooky connection, created deliberately, again and again, thousands of times every second. That is almost the entire toolkit. One of the great theorems of quantum computing tells us that a small collection of gates like these can be combined to perform any quantum computation allowed by the laws of physics. Just as ordinary logic gates can build every classical program, these quantum gates can build every quantum algorithm. Everything else is simply arrangement, and those arrangements have their own elegant notation. A quantum circuit looks remarkably like a page of sheet music. Each horizontal line represents 1 qubit. Time flows from left to right. The gates appear like musical notes placed along the staff. A Hadamard gate opens a superposition. C0 gates weave qubits together through entanglement. Phase gates quietly adjust the hidden relationships between amplitudes. And at the very end comes measurement, the only part the outside world ever sees. The length of that circuit matters enormously. Every extra operation gives the surrounding environment more time to disturb the fragile quantum state, a challenge we will soon meet under the name decoherence. And the no cloning theorem adds another restriction. Unlike classical information, quantum information cannot simply be copied halfway through a computation. There is no copy and paste, no duplicate backup. Every qubit follows its own unique journey from beginning to end. Before we continue, one reassuring point. Nobody programs today's quantum computers by drawing Bloch spheres or calculating rotations by hand. Most researchers write ordinary code, usually in Python, using software frameworks that we will explore later in this documentary. Those tools translate the programmer's instructions into microwave pulses, laser flashes, and other physical operations that control real qubits. The underlying grammar is unfamiliar, but the programming experience is often surprisingly familiar. By 1994, the foundations were in place. Scientists understood the theory of a universal quantum computer. They understood its basic language, and yet, most people still viewed quantum computing as an interesting academic curiosity. That would soon change. A mathematician working at Bell Labs had just finished reading Daniel Simon's paper. One idea refused to leave his mind, and within a matter of days, that idea would transform quantum computing from a scientific curiosity into an issue of global security. Chapter 12: The Earthquake. To understand why this was such an earthquake, we first have to understand the ground it shattered. In 1977, three researchers at MIT, Ron Reeves, Adi Shamir, and Leonard Adleman, introduced a cryptographic system that solved what seemed like an impossible problem. How can two strangers exchange secret information over a line that everyone else can listen to? Their answer became known as RSA. Imagine a padlock. I can send an open padlock to anyone in the world. That is my public key. Anyone can place a message inside, snap the padlock shut, and send it back to me. But closing a padlock and opening one are two very different things. Only I have the key. RSA works in much the same way. Its mathematical padlock is multiplication. Take two enormous prime numbers, each hundreds of digits long, and multiply them together. That multiplication is easy. Your phone can do it in a tiny fraction of a second. The result becomes the public lock. But going the other way is a completely different challenge. Start with that enormous product and try to recover the two original prime numbers. That process is called factoring. And factoring belongs to the family of exponential problems we met back in Chapter 4. Multiplying is like stepping off a cliff. Factoring is like climbing back up. History hides one fascinating twist. In 1973, 4 years before RSA became public, a British mathematician named Clifford Cocks developed essentially the same idea while working at GCHQ, the United Kingdom's Signals Intelligence Agency. His work remained classified for 24 years. In other words, the spies had public key cryptography long before the public ever did. So just how steep is this mathematical cliff? The best classical factoring algorithm ever discovered is called the number field sieve. In 2020, it was used to factor an 829-bit number, a world record that required roughly 2,700 years of combined processor core time. Today, the standard encryption protecting much of the internet uses 2048-bit keys. That is a vastly harder problem. As the numbers grow larger, the work grows explosively. On today's classical computers, factoring a typical 2048-bit RSA key is considered completely impractical, far beyond anything we can realistically achieve. That assumption became the foundation of modern digital security. Online banking, shopping, government communications, the little padlock icon in your web browser. All of it depends on one belief, that factoring large numbers is simply too difficult. To be clear, nobody has ever proved that it is impossible. Mathematicians have simply tried for centuries, failed every time, and built modern civilization on the expectation that the pattern would continue. Then came Peter Shor. Shor was a mathematician at Bell Labs, the same place that gave us the transistor, Claude Shannon's bit, and so many ideas in this story. In 1994, he read Daniel Simon's paper. It described a quantum method for uncovering hidden patterns through interference, and Shor noticed something remarkable. A result from 19th century number theory shows that factoring can be transformed into a completely different problem. Instead of finding prime factors directly, you only need to discover the period of a repeating mathematical pattern. Let's build some intuition. Imagine a clock. After 12 comes 1 again. The numbers repeat in a cycle. Number theory uses a similar idea. Choose a large number n that you want to factor. Now repeatedly raise another number to higher and higher powers, always wrapping the result around n. Eventually the sequence starts repeating. It settles into a rhythm. That repeating rhythm is called the period. And hidden inside that period is the information needed to uncover n's prime factors. The problem is that the rhythm can be unimaginably long. For a 617-digit number, a classical computer has no better strategy than checking the sequence step by step. One calculation after another. The cliff is still there. It is simply wearing different clothes. Now comes Shor's breakthrough. And notice something remarkable. Everything that follows uses ideas you already understand. First, Hadamard gates place a register of qubits into a superposition containing an enormous range of possible exponents, all at the same time. Next, the quantum circuit performs the clock arithmetic across every one of those possibilities simultaneously. Each computational path carries its own amplitude, like a musician carrying its own beat. Hidden inside those amplitudes is the rhythm we are searching for. Finally comes the quantum Fourier transform. Think of it as a machine with an extraordinary ear for rhythm. A regular Fourier transform lets music software separate a chord into its individual notes. The quantum version does something closely related. Paths that do not match the true period arrive out of phase and cancel each other away. Dark stripes. The paths that do match the hidden rhythm arrive perfectly aligned. Their amplitudes reinforce each other. Bright stripes. It is the hall of engineered slits from Chapter 8, carefully tuned to hear a single mathematical rhythm. Then comes the measurement, and with high probability, the quantum computer reveals the period. Run the algorithm a few more times to confirm the result. The entire process scales in polynomial time. That difference is almost impossible to overstate. For some problems, it is the difference between waiting longer than the age of the universe and finishing within a practical amount of time. Notice what made all of this possible because it captures the honest heart of this entire film. Factoring has hidden structure. Buried deep inside the mathematics is a repeating rhythm that quantum interference can recognize. Shor did not build a machine that tries every possible divisor. Instead, he found the rhythm hidden inside the arithmetic and built a machine that could hear it. Problems that do not contain this kind of hidden structure offer nothing for interference to lock onto. They have no rhythm to hear. That single idea separates real quantum computing from almost every exaggerated headline you will ever read. Shor presented his algorithm in the spring of 1994. The reaction spread through physics and computer science like a pressure wave. Then it reached places that rarely publish research papers: intelligence agencies, security organizations, governments. Within weeks, they understood what this meant. A sufficiently large quantum computer would not simply weaken modern cryptography. It could break much of it. Even worse, it could expose encrypted information that had been collected years earlier. Quantum computing stopped being an interesting theoretical idea that day. It became a matter of national security. Research funding appeared. New laboratories opened. Governments launched major programs. The global race we'll explore later in this film. The billions of dollars, the satellites, the national strategies, can all be traced back to just 4 pages of mathematics. Now comes the honest reality check. This is where hype usually begins. And we promised from the very start to separate proven facts from predictions. Here is the established fact. Shor's algorithm is mathematically correct. It is a proven theorem. If you had a sufficiently large, fault-tolerant quantum computer, it could factor large numbers in polynomial time. That is as certain as the mathematics itself. Now, the engineering reality. That computer does not exist. The largest numbers ever factored by genuine implementations of Shor's algorithm on real quantum hardware are 15, demonstrated in 2001, and 21, demonstrated in 2012. 15, 21, numbers a child could factor while eating lunch. From time to time, you may see headlines claiming that much larger numbers have been factored on quantum computers. Look closely, and the story usually changes. The demonstrations rely on shortcuts, special mathematical structure, or classical assistance that cannot scale to real-world encryption. They make impressive headlines. They do not demonstrate Shor's algorithm at practical scale. The pattern repeats often enough that it is worth recognizing. In 2022, one widely discussed preprint claimed large-scale quantum factoring using a controversial classical technique. Experts challenged the result within days. In 2024, headlines claimed a quantum annealer had broken military-grade encryption. The actual demonstration involved only a tiny 22-bit example. Small numbers, non-scalable methods, big headlines. Once you know the pattern, it becomes much easier to spot. Now for the forecast, and this is a forecast, not an established fact. How large would a quantum computer need to be to threaten RSA 2048? In 2019, researchers Craig Gidney and Martin Eckerow published one of the most careful engineering estimates available. Their analysis suggested roughly 20 million noisy physical qubits, running for about 8 hours, assuming realistic error rates. Then, in 2025, Gidney revisited the calculation using improved techniques. The estimate dropped dramatically to fewer than 1 million noisy physical qubits running for less than a week. Today's largest quantum processors contain roughly 1,000 physical qubits. So the gap is still enormous, about 3 orders of magnitude. But notice something equally important. In just 6 years, improved algorithms reduced the estimated hardware requirement by roughly a factor of 20, while the hardware itself improved by about an order of magnitude. The mountain is being climbed from both sides. When will those two climbers finally meet? Nobody knows. Later in this film, we'll examine the expert predictions carefully and we'll label them for what they are: predictions, not facts. One important question still remains. Shor's algorithm works because factoring contains a hidden rhythm. But what about problems with no hidden structure at all? What about searching through a completely random haystack? Just 2 years later, down the hall at the same Bell Labs, a researcher named Love Grover answered that question. And his answer draws perhaps the clearest boundary around what quantum computers can and cannot do. Chapter 13. The Needle, the Haystack, and the Honest Map. Love Grover's 1996 problem is almost unbelievably simple. Imagine a phone book with 1 million names. Now shuffle every page into a completely random order. You have a phone number in your hand. Your task is to find the matching name. There is no pattern, no hidden rhythm, no shortcut. For a classical computer, the only option is brute force. Check one entry, then the next, then the next. On average, you'll search about 500,000 entries before finding the right one. Grover discovered a quantum algorithm that changes the picture. Instead of needing about 1 million checks, it needs only about 1,000. Not 1 million, not 500,000, about the square root of 1 million. And by now, you already understand every idea that makes it work. First, apply Hadamard gates. The qubits spread into an equal superposition across every possible entry. Each possibility receives a tiny amount of amplitude. Every amplitude starts perfectly aligned, like millions of clock hands all pointing in the same direction. Next comes something called the oracle. Think of it as a circuit that recognizes exactly one thing, the correct answer. When it finds that answer, it does something surprisingly subtle. It flips only the phase of the correct entry. Nothing else changes. Remember the silent Z gate from the previous chapter? This is where that idea becomes essential. After the oracle finishes, every entry is still equally likely if you measure immediately. Nothing visible has changed, except one hidden clock hand is now pointing the opposite way, a mark that no ordinary measurement can reveal. Now comes Grover's second step. It has a complicated mathematical name, inversion, about the average. Fortunately, the idea is much simpler than the name. Imagine every clock hand pivoting around the average direction of all the others. The millions of ordinary hands barely move, but the one hand pointing backward is far away from that average. So it swings dramatically upward. Its amplitude grows. Then the process repeats. Mark, pivot, mark, pivot. Each round transfers a little more amplitude away from the haystack and into the needle. Perhaps the best way to picture it is a child on a swing. One push does very little, but if every push arrives at exactly the right moment, each one adds to the last. The swing climbs higher and higher and higher. After roughly 1,000 perfectly timed pushes, the square root of 1 million, almost all the amplitude has gathered around the correct answer. Measure the qubits, and the needle is very likely to fall straight into your hand. The swing analogy also teaches an important lesson. Push for too long and the swing starts coming back down. Like Grover's algorithm behaves the same way. Run it past its optimal stopping point and the probability of getting the correct answer begins to fall again. That is a genuinely quantum effect. The algorithm has a best moment to stop. Miss that moment and performance gets worse. One more detail keeps the analogy honest. Every push requires running the entire oracle circuit. So Grover's speedup measures the number of queries, not the total cost of each query. And the improvement is always quadratic. No more. 1 million possibilities become about 1,000. A quintillion possibilities become about 1 billion. That is an extraordinary improvement. But it is not magical. That phrase, not magical, is one of the most important in this entire film, because it defines the real limits of quantum computing. Take cryptography. Grover's algorithm affects symmetric encryption, systems like AES. In practice, it effectively cuts the security of a key roughly in half. Fortunately, the solution is remarkably simple. Use longer keys. Replace AES 128 with AES 256, and Grover's advantage largely disappears. The search becomes so enormous that even a quantum computer would require an impractical amount of time, especially because Grover's iterations must be performed mostly one after another. They cannot be massively parallelized in the same way as many classical searches. Compare that with Shor's algorithm. Shor directly threatens public key cryptography. Grover only weakens symmetric cryptography, and that weakness is already well understood and relatively easy to defend against. That single distinction dissolves much of the panic surrounding quantum code-breaking. Grover's algorithm also marks an important boundary, and this boundary is not an opinion. It is a proven mathematical result. For an unstructured search, where the only way to learn anything is to keep checking possibilities, no quantum algorithm can do fundamentally better than Grover's square root speedup. That is an established theorem, not a prediction, not a belief, a theorem. No future breakthrough will turn an unstructured haystack into another Shor-style revolution, because a haystack has no hidden rhythm. And without a rhythm, there's nothing for quantum interference to hear. So now let's draw an honest map of quantum algorithms. What belongs on that map and what belongs in the fine print. The deepest and most important territory is exactly where the story began, simulating quantum systems, molecules, new materials, exotic forms of matter. This is the problem Richard Feynman pointed to in 1981. Here, the advantage is natural, and for many important problems, it can be exponential. The workhorse behind these simulations is a technique called phase estimation. You can think of it as an extraordinarily precise ear built from the same mathematical ideas, the Fourier transform, that powered Shor's algorithm. Instead of listening for a hidden rhythm in numbers, phase estimation listens for the energy of a quantum system. It can determine molecular energy levels with a precision that classical methods cannot efficiently match. The theory is well established, the hardware is still catching up. Now we move into more tempting territory, and this is where the map needs warning labels. In 2009, 3 researchers, Aram Harrow, Avinatan Hasidim, and Seth Lloyd, introduced an algorithm now known as HHL. It promised an exponential speedup for solving enormous systems of linear equations. That may sound abstract, but linear equations sit underneath engineering, physics, finance, and much of modern machine learning. The headlines almost wrote themselves. But the fine print mattered. The algorithm assumes that an enormous amount of classical data can be loaded into quantum amplitudes almost for free. In many realistic situations, preparing the data costs more than solving the problem. Then comes another limitation. The result is not an ordinary list of numbers. It is a quantum state. And because of measurement, you cannot simply read out the entire answer. You can only sample it through the same measurement bottleneck we've discussed throughout this film. Under very specific conditions, HHL could be transformative. Outside those conditions, the promised speedup can disappear. So whenever you hear about a dramatic quantum algorithm, ask 2 simple questions. How does the data get in? And how does the answer get out? Those 2 questions will make you a more careful reader than many headlines. Now for one of the best lessons in all of computer science. In 2018, an 18-year-old undergraduate at the University of Texas named Ewin Tang received a thesis problem. The goal was to prove that a famous quantum recommendation algorithm, the kind of algorithm that predicts what movie or song you might enjoy next, had a speedup that no classical algorithm could match. She spent months studying it, and then she surprised everyone. Instead of proving the quantum advantage, she found a classical algorithm that achieved essentially the same performance. The quantum advantage vanished. The field now has a name for this: dequantization. And it did not stop there. Over the following years, several other claimed quantum machine learning advantages were matched by new classical algorithms. The lesson is an important one. This race has 2 competitors. Quantum algorithms continue improving, but so do classical algorithms. Any claimed quantum advantage remains provisional until the best classical researchers have had their chance to respond. Remember that lesson. We'll see it appear again later in this film. Finally, we reach the frontier. The part of the map still covered in fog. These are the variational algorithms. Names like VQE and QAOA, rather than relying on one large, perfect quantum computer, they combine a small, noisy quantum processor with an ordinary classical computer. The classical computer suggests possible solutions. The quantum processor evaluates them. Then the process repeats, back and forth, again and again. These algorithms were designed specifically for the imperfect quantum hardware available today. They may help solve useful problems in chemistry or optimization before fully fault-tolerant quantum computers arrive. They may. That word matters. At present, no general quantum advantage has been proven for these methods. The honest label is simple, promising, but unproven. And history has taught us that promising heuristics can disappoint. Now step back and look at the map as a whole. A pattern emerges. Quantum computers are not universally faster, they are specialists. Remarkably powerful when a problem contains the right kind of hidden structure, rhythms, energy landscapes, or quantum amplitudes. They offer a quadratic improvement for unstructured search. And for many everyday computational problems, they may offer little or no advantage at all. Computer scientists describe this using a complexity class called BQP. It represents the problems that quantum computers are believed to solve efficiently. Most experts believe BQP extends beyond the reach of classical computers in important but very specific directions. Just as importantly, most experts do not believe it includes the famous NP-complete problems, such as finding the exact optimal solution to the traveling salesman problem. There is no proof either way, but the expert consensus is remarkably consistent. The claim that quantum computers will solve every hard problem is not scientific optimism, it is fiction. So the picture becomes clear. A quantum computer is a specialist. Brilliant, powerful, narrow in its strengths, and, as we're about to discover, almost unimaginably fragile. Because everything we've explored over the last 4 chapters quietly assumed that qubits behave exactly as we want them to. In the real world, they do not. By the mid-1990s, many leading researchers believed this was the obstacle that would stop the entire field. Several of the most respected scientists in quantum computing said so publicly. What happened next became one of the greatest engineering breakthroughs in modern science. And yet, outside the field, almost nobody knows the story. Chapter 14. The Enemy Within. The universe, it turns out, is incredibly curious. A qubit in superposition is holding a secret, those delicate amplitudes, those hidden phase relationships, and almost everything around it is trying to uncover that secret. A stray photon glances off it, a wandering gas molecule drifts too close. The atoms inside the chip vibrate with heat. Sometimes a cosmic ray, an actual particle from deep space, crashes into the processor. Yes, that really happens. And yes, it can ruin a quantum calculation. Every disturbance acts like the detector in the double-slit experiment. The environment learns something about the qubit, and the instant that information leaks away, the superposition begins to fade. Not with a dramatic collapse, it slowly leaks into the surrounding world. The delicate phases lose their alignment. The hidden clock hands drift out of sync. Physicists call this decoherence. It is the reason our everyday world looks classical. Large, warm objects are constantly being measured by everything around them. Every second, every moment. Schrödinger's famous cat never gets the chance to be both alive and dead. So, how long can a qubit keep its secret? For superconducting circuits, the answer is usually between a few microseconds and a few hundred microseconds. Trapped ions perform much better. Under carefully controlled conditions, they can preserve quantum information for seconds, sometimes even minutes. But regardless of the technology, every quantum computation is like a sandcastle, and the tide is always coming in. The problem gets worse. Every quantum gate is slightly imperfect. Every operation introduces a tiny error of its own. Today's best 2-qubit gates fail roughly once in every 1,000 operations, sometimes a little better. That sounds impressive. Until you remember that Shor's algorithm, running on a real cryptographic key, would require trillions of operations. Do the math. It seems hopeless. The obvious solution comes from classical computing, redundancy. Store every bit 3 times. If one changes unexpectedly, let the other 2 outvote it. Simple, reliable, and completely impossible for quantum information. Every part of that strategy is blocked by laws we've already discovered. You cannot copy a qubit. The no-cloning theorem forbids it. You cannot stop and inspect it during the computation. Measurement would collapse the very superposition you're trying to protect. And quantum errors are far more complicated than ordinary bit flips. Sometimes the probabilities drift. Sometimes the hidden phases drift instead. Those phase errors are especially dangerous because a normal measurement cannot even see them. Instead of a clean 0 becoming a 1, there is an endless spectrum of tiny mistakes. By the mid-1990s, many respected physicists reached a sobering conclusion. Quantum computing was a beautiful idea, but noise would make it impossible. Even Rolf Landauer, the physicist who taught us that information is physical, believed the field deserved deep skepticism. He argued that every quantum computing paper should carry a warning label. This was not fringe criticism. It was the sensible position. Then, in 1995, Peter Shor returned with another astonishing breakthrough. And independently, Andrew Steen at Oxford arrived at the same destination by a different path. Together, they found a doorway where everyone else had seen only a wall. The insight sounds almost impossible. Protect the information by making sure no single qubit ever contains it. Instead of storing one logical qubit inside one physical qubit, spread it across many physical qubits using entanglement. Not copied. That would violate quantum mechanics. Entangled. Distributed across the entire system so that no individual qubit knows the complete quantum state. Then ask a completely different kind of question. Never ask, what state are you in? Instead ask, do these two qubits still agree with each other? These are called parity checks. Remarkably, quantum mechanics allows them. They reveal whether an error has occurred without revealing the quantum information itself. The secret stays hidden, but the damage becomes visible. The pattern of those parity checks identifies exactly where error happened, where the error it was, and what kind of error it was. That pattern is called the syndrome. Read the syndrome, apply the opposite correction, and the error disappears while the logical qubit itself remains untouched. Imagine three friends sharing a secret. You are forbidden from asking any of them what the secret is. The only question you may ask is, do the two of you still agree? If one friend answers differently, you've found the mistake without ever hearing the secret itself. That captures the basic idea. But the real quantum version is even stranger. Quantum computers must detect two completely different kinds of errors at the same time: ordinary bit flips and hidden phase flips. Shor's original error-correcting code used 9 physical qubits to protect one logical qubit, guarding against both kinds of mistakes simultaneously. And one final detail makes the whole idea truly extraordinary. In the analogy, each friend already knows the secret. Real qubits do not. No individual qubit contains the information. The quantum state exists only in the entangled relationships between them, not in any single part, but only in the whole. Stranger than any analogy, and exactly why quantum error correction works. The idea advanced remarkably fast. Andrew Steen developed a 7-qubit error-correcting code. Then, in 1997, Alexei Kitaev introduced the design that would shape the future, the surface code. Imagine physical qubits arranged across a simple checkerboard. Each parity check involves only neighboring qubits. No complicated long-distance connections, no impossible wiring, just a clean, repeating pattern that engineers could actually build. When you see photographs of modern quantum processors laid out as neat grids, you're looking at Kitaev's checkerboard, waiting for the game to begin. Then came the breakthrough that changed everything. Not another clever idea, a theorem. Several research groups, including Dorit Aharonov and Michael Ben-Or, Emmanuel Nil, Raymond Laflamme, and Wojciech Zurek, and Alexei Kitaev proved what is now called the threshold theorem. Many researchers consider it the most important result in the entire field. Its message is astonishing. If the error rate of every physical operation can be pushed below a critical threshold for surface codes, roughly one mistake in every 100 operations, then something remarkable happens. As you build larger and larger error-correcting codes, the logical error rate does not merely improve. It falls exponentially. Below the threshold, size stops being the enemy. It becomes the solution. Every expansion of the code makes the logical qubit dramatically more reliable. Grow it far enough, and the probability of failure can become so small that, in principle, a calculation could run longer than the age of the universe without a logical error. That is an established mathematical theorem. It does rely on important assumptions. Most importantly, it assumes errors occur mostly independently, not as large, coordinated failures. We'll return to that point when we meet the skeptics later in this film. But the conclusion remains. No known law of physics forbids large-scale quantum computing. The remaining challenge is engineering, and that engineering comes with a staggering price. The field calls it overhead. One reliable logical qubit may require hundreds or even 1,000 physical qubits working together. Imagine an entire stadium filled with imperfect players, all cooperating to protect a single perfect seat. Then add another challenge. Every parity check must be decoded instantly by powerful classical computers. And there is another subtle cost. Some essential quantum gates cannot be formed directly inside the code. Instead, they depend on specially prepared quantum resources known as magic states. Think of them as rare, carefully refined fuel consumed by fault-tolerant quantum computers whenever they need their most powerful operations. Look back at the million physical qubit machine we discussed earlier. Seen from another perspective, it is only a few thousand logical qubits, each wrapped in enormous layers of protection. For more than 25 years, all of this remained purely theoretical. Real machines operated above the threshold. In that regime, adding more qubits only created more opportunities for failure. Error correction actually made things worse. Crossing below the threshold became the field's Rubicon, and during the mid-2020s, that crossing finally happened. These were engineering milestones, not practical quantum computers, but genuine proof that the mathematics worked. In December 2023, a Harvard-led team using Quera's neutral atom technology demonstrated circuits running on 48 logical qubits encoded across 280 atoms. It was the first demonstration of a true collection of logical qubits working together. In 2024, Microsoft and Quantinuum showed logical qubits built from trapped ions whose error rates were dramatically lower than those of the physical qubits beneath them. Then in December 2024, Google unveiled its Willow processor. And for the first time, the famous prediction of the threshold theorem appeared directly in experimental data. As the surface code patches grew from distance 3 to 5 to 7, the logical error rate fell almost exactly as the theory predicted. Roughly cut in half with every increase in code distance. Exponential error suppression. On real hardware. A logical qubit surviving longer than any physical qubit inside the processor. The theorem had stepped out of mathematics and into the laboratory. Since then, research groups have continued improving the designs. By early 2026, reports described systems operating with roughly 100 logical qubits at once. The threshold theorem is no longer just a promise, it is becoming engineering reality, one checkerboard patch at a time. Rolf Landauer never lived to witness it. He helped launch the field. He challenged its assumptions, he demanded its skepticism, and he died in 1999, long before these experimental curves existed. In a way, every graph showing successful error correction is a quiet reply to him. The journey is far from over. Between today's logical qubits and the fault-tolerant machines powerful enough to transform science lies years of difficult engineering. No serious researcher disputes that. But one question has already been answered. It is no longer, can this machine exist? Now the question is, what kind of machine will it be? And on that question, the world's laboratories have divided into rival camps, 7 different technologies, 7 different visions, each betting billions that theirs will become the future of quantum computing. Chapter 15, 7 bodies for 1 mind. Nature is remarkably generous. There are countless physical systems that naturally provide 2 stable quantum states, a perfect 0 and a perfect 1. So when scientists ask, what should a qubit actually be made of? There is no single correct answer. There are many. Over the years, the world's laboratories have divided into rival schools, 3 leading contenders, 3 ambitious challengers, and 1 beautiful heresy. As we explore them, judge each technology by the measurements that truly matter. How often do its quantum gates make mistakes? Count the 9s. 99 point what? How fast can the gates operate? How easily can distant qubits communicate? How long can quantum coherence survive? And perhaps most importantly, can the technology eventually scale into the thousands or even millions of protected qubits that a practical quantum computer will require? Keep one simple rule in mind. Count the nines, not the qubits. That single habit will protect you from a decade of impressive-looking press releases. The first major contender is superconducting circuits. These are today's incumbents, championed by Google, IBM, and many other laboratories around the world. Cool certain metals to temperatures just above absolute zero, and something extraordinary happens. Their electrical resistance disappears completely. Build tiny loops interrupted by microscopic junctions, and those circuits begin behaving like artificial atoms, complete with their own quantum energy levels. Instead of growing atoms, engineers manufacture them using the same lithography techniques developed by the semiconductor industry. They can fabricate thousands at once. Their greatest strength is speed. Quantum gates finish in mere nanoseconds, among the fastest operations in the field. But speed comes at a price. These qubits survive only inside one of the most extreme machines ever built, a dilution refrigerator, the golden chandelier we saw at the beginning of this film, a towering stack of ever colder stages, each colder than the one above, until the bottom reaches only 10 to 15 thousandths of a degree above absolute zero. That temperature is almost impossible to imagine. Deep space itself, warmed by the faint afterglow of the Big Bang, rests at about 2.7 degrees above absolute zero. These quantum processors operate nearly 200 times colder. As far as we know, the coldest cubic centimeters in the entire universe exist inside machines like these. Yet another challenge waits there. Every qubit currently requires its own delicate control wiring, threaded all the way down through the refrigerator. As processors grow larger, those wires begin to resemble an impossible forest. Engineers are now racing to build cryogenic control electronics that can survive inside the refrigerator itself, reducing the wiring before it overwhelms the machine. The second leading technology is trapped ions. If superconducting circuits are the speed specialists, trapped ions are the perfectionists. Companies like Quantinuum and IonQ have built on decades of atomic physics research. Here, the qubits are not artificial. They are real atoms. Single-charged atoms levitating inside an ultra-high vacuum, held perfectly in place by rapidly oscillating electric fields inside a device known as a Paul trap. Lasers perform every operation, preparing the qubits, manipulating them, reading them. Their greatest advantage is perfection. Every ion of the same element is fundamentally identical. No manufacturing defects, no microscopic imperfections. An atom created today is indistinguishable from one created a billion years ago. Their quantum coherence can last for seconds, sometimes even longer. And trapped ion systems routinely achieve some of the highest gate fidelities ever demonstrated. 2-qubit operations exceeding 99.9% and steadily improving. Another remarkable advantage is communication. Because the ions share collective vibrations, almost any qubit can interact with almost any other. No nearest neighbor limitation, no checkerboard restrictions. But perfection has its own cost: speed. These gates operate thousands of times more slowly than superconducting circuits, and scaling beyond a few hundred ions becomes an enormous engineering challenge. Future systems will likely require entire networks of ion traps, connected together by single photons carrying quantum information from one module to another. Elegant in theory, exceptionally demanding in practice. The third leading contender, and perhaps the fastest rising, is neutral atoms. Companies like Qwera and Pascal, along with research groups at Harvard and Caltech, are leading this approach. Unlike trapped ions, these atoms carry no electric charge. Instead of electric fields, they are held in place by optical tweezers. Highly focused laser beams, acting like invisible chopsticks made entirely of light. Each beam traps a single atom, and those atoms can be rearranged during a computation into almost any pattern the algorithm requires. The chopstick analogy helps, but it has one important limitation. Nothing physical ever touches the atom. It simply rests inside a carefully shaped landscape of light. To create entanglement, scientists briefly excite an atom into what is called a Rydberg state. Its outer electron expands dramatically, sometimes more than 1,000 times farther from the nucleus than normal. For a brief moment, the atom becomes highly sensitive to its neighbors. Interactions that were impossible suddenly become easy. Then the atom quietly returns to its ordinary state. This architecture scales remarkably well. In 2024, Caltech demonstrated an array containing more than 6,000 optical tweezers, and it was this very platform that produced the 48 logical qubits we discussed in the previous chapter. Watch this technology closely, it is advancing quickly. Now come the dark horses. The first is photonics, championed by companies like PsiQuantum and Xanadu. Here, the qubit is not an atom, it is a single particle of light, a photon traveling through microscopic waveguides etched into glass. Photons have extraordinary advantages. They barely interact with the environment. They naturally travel long distances, and they are the obvious building blocks for future quantum communication networks. But they also bring difficult problems. Photons rarely interact with one another. Creating reliable 2-qubit gates requires ingenious measurement-based techniques that often succeed only probabilistically. Photons can also be lost during transmission. Every missing photon becomes a missing qubit, which means enormous amounts of redundancy are required. And despite the common claim that photonic systems operate at room temperature, there is important fine print. The delicate single photon detectors still need cryogenic cooling. PsiQuantum has taken perhaps the boldest gamble in the entire industry. Rather than building a long series of increasingly capable prototypes, they intend to leap directly toward a utility-scale quantum computer. Facilities have already been announced in Brisbane and Chicago. For now, they remain ambitious plans, not completed machines. Another challenger is silicon spin qubits, developed by Intel, research groups in Delft and New South Wales, and startups such as Dirac. Here, a single electron is trapped inside a tiny semiconductor structure, similar to a transistor. Its quantum spin becomes the qubit. The attraction is obvious. These devices are built using manufacturing techniques already capable of producing billions of transistors. They are incredibly small. Where superconducting processors might fit dozens of qubits, silicon could someday fit millions. Since 2022, their gate fidelities have surpassed the important 99% threshold. Some reports are now approaching 4 nines. Their greatest challenge is consistency. Every tiny quantum dot must behave almost identically, and somehow, millions of them must all be wired together. Then there is D-Wave. Its machines belong to a different family altogether. Instead of running universal quantum circuits, they perform quantum annealing. Thousands of qubits cooperate to relax naturally toward good solutions for optimization problems. It is a specialized approach designed for a very specific class of tasks. Claims of quantum advantage remain actively debated. Closely related are analog quantum simulators. Rather than programming a computer to imitate nature, scientists build physical systems that are the phenomenon they want to study. Cold atoms arranged to behave like exotic magnetic materials. Artificial quantum matter created inside the laboratory. These machines are already helping researchers explore questions about magnetism, superconductivity, and entirely new phases of matter. Finally, there is the most elegant idea of them all, and also the most controversial, topological qubits, pursued primarily by Microsoft. The dream is breathtaking. Store quantum information, not inside any individual particle, but inside the overall braided arrangement of exotic quantum objects known as Majorana modes. If successful, local disturbances would simply be unable to damage the information. The protection would be built directly into the geometry of the qubit itself. Error correction woven into the hardware. It is one of the most beautiful ideas in modern physics, and one of the least proven. A major research paper published in 2018 was later retracted in 2021. Then, in early 25, Microsoft announced its Majorana 1 chip. The announcement generated enormous excitement. It also generated equally strong scientific skepticism. Even the reviewers of the published paper noted that the evidence did not yet demonstrate a functioning topological qubit. Both statements are true. If this approach succeeds, it could transform the future of quantum computing. And today, it has not yet been conclusively demonstrated. That is the fairest summary anyone can honestly give. So, which technology will ultimately win? The truthful answer is, nobody knows. The future may not belong to a single architecture at all. Different quantum computers may excel at different jobs, and there are still other technologies, such as diamond-based quantum systems, that we'll meet later when we explore quantum sensing. But now that you've met the contenders, we can finally ask the question everyone wants answered. Who is actually winning? To find out, we need to visit the scoreboard. And the scoreboard is a battlefield. Chapter 16, The Scoreboard Wars. In September 2019, something unusual happened. A scientific paper appeared where it was never supposed to appear. For a brief moment, it was posted on a NASA web server. Then, it vanished, but not before people took screenshots. Within hours, technology news outlets around the world were reporting an extraordinary claim. Google had built a quantum computer that had done something no classical supercomputer on Earth could match. Weeks before the paper's official publication, the embargo had collapsed. Competitors were scrambling. When the paper finally appeared that October on the cover of Nature, it carried one of the most controversial phrases in modern science: quantum supremacy. The term had been introduced in 2012 by Caltech physicist John Preskill. Despite the dramatic name, its meaning is actually very specific. Quantum supremacy is simply the moment when a quantum computer performs any calculation, even one with no practical value, that lies beyond the reach of the best classical computer. Think of the Wright brothers. Their first airplane flew only 120 feet. It changed history, even though nobody wanted to buy a ticket. Preskill also gave a name to the era we are living in today. NISQ, Noisy Intermediate Scale Quantum, an honest description of today's imperfect machines. He also made another important distinction. Quantum supremacy is a scientific milestone. Quantum advantage, sometimes called quantum utility, is something much more valuable. That is the moment when a quantum computer solves a real-world problem better than the best classical alternative. Keep those two ideas separate. Press releases often do not. Google's processor, called Sycamore, contained 53 working superconducting qubits. Its task was known as random circuit sampling. In simple terms, the processor generated samples from an extremely complicated quantum probability distribution. Not useful, but exceptionally difficult for classical computers to reproduce. Google reported an astonishing comparison. The quantum processor finished in about 200 seconds. They estimated the world's fastest supercomputer would require 10,000 years. It was an extraordinary claim, and the response came almost immediately. IBM disagreed. Using more efficient algorithms and clever management of storage, they argued the same calculation could be completed in roughly 2.5 days. Then, something even more interesting happened. The strongest challenge did not come from another quantum computer. It came from classical computer scientists. Just as Yuan Tang had shown years earlier, classical algorithms continued improving. Tensor network methods, running on powerful GPU clusters and supercomputers, steadily closed the gap. Within only a few years, the supposedly impossible benchmark had been reproduced in hours. Eventually, the original 10,000-year estimate no longer held. Both parts of the story are true. Sycamore represented a remarkable engineering achievement, and its original supremacy claim did not survive the relentless progress of classical computing. Remember this pattern, because it keeps happening. In 2020, China's Zhujiang photonic quantum computer announced its own sampling supremacy result. Classical algorithms improved, the gap narrowed, researchers raised the benchmark again. The cycle repeated. In 2023, IBM published a striking Nature paper describing what it called quantum utility, a simulation of magnetic materials using 127 qubits. The result relied heavily on error mitigation, not true quantum error correction, but statistical techniques applied after the computation to reduce mistakes. Within months, classical methods caught up again. Then came Google's Willow processor in December 2024. Its error correction results, as we saw in the previous chapter, were genuine milestones. But alongside those achievements, Google also reported another benchmark, one they estimated would require 10 septillion years on classical hardware. Treat numbers like that carefully. History has taught us a lesson. They are opening bids, not final verdicts. Every major benchmark in this field has eventually been challenged by better classical algorithms. In 2025, D-Wave announced quantum advantage for a simulation of magnetic materials published in Science. Within weeks, classical researchers offered competing analyses. The debate continued. Later that same year, Google introduced another result called quantum echoes. This one attracted attention for a different reason. It claimed an advantage on a physically meaningful quantity, whose answer could actually be verified independently. According to Google's report, the calculation ran thousands of times faster than a leading supercomputer. As of early 2026, the scientific community is still testing that claim, exactly as it should. Because in quantum computing, the scoreboard is never final. Every result invites another challenge. Every breakthrough demands another test. And every claimed victory must survive both experiment and the relentless creativity of classical computing. So, what should we make of all this? This back and forth is not a scandal, and it is not failure. It is science, working exactly as it should. Every time a quantum team announces a breakthrough, the world's best classical computer scientists immediately try to prove them wrong. They build faster algorithms, they find smarter shortcuts, they test every claim from every angle. Then, the quantum researchers respond. The classical methods improve, the quantum hardware improves, both sides push each other forward, and with every round, our understanding becomes a little sharper. Back in chapter 13, we called this the Leapfrog dance, and that dance will continue for years. So, what does the honest scoreboard actually say? It can be summarized in just 3 simple statements. First, for carefully designed benchmark experiments, quantum computers have probably achieved quantum advantage, but those results have also been challenged, tested, and debated. Some claims have survived, others have not. The discussion is still ongoing. Second, for problems that people would actually pay to solve, where a quantum computer clearly performs better or more cheaply than every classical alternative, that milestone has not been reached. Not yet. As of today, no quantum computer has demonstrated a clear commercial advantage, anywhere. And third, if you want to know where the real race is happening, look at error correction. Not flashy benchmarks, not dramatic headlines. Error correction. The below-threshold demonstrations achieved between 2023 and 2026 have been reproduced across multiple hardware platforms. Quietly, they may prove far more important than every quantum supremacy headline combined. So, what comes next? According to the companies building these machines, the next major milestone is fault-tolerant quantum computing. IBM has published a roadmap for a system called Starling, targeting around 2029 with roughly 200 logical qubits. Google's leadership has spoken about useful error-corrected applications within a similar time frame. Several other companies have announced comparable goals. But remember what these are. They are corporate roadmaps, real plans made by serious engineers, backed by billions of dollars. But still, plans. Technology roadmaps have a long history of slipping behind schedule. Meanwhile, the United States Defense Research Agency, DARPA, is taking a very different approach. Instead of making promises, DARPA is asking a simple question. Can any of these technologies actually deliver? To find out, it launched the Quantum Benchmarking Initiative. Its mission is straightforward. Independently verify whether any quantum computing platform can reach practical utility by 2033. Around a dozen companies have already advanced through the program's early stages. And that should tell you something important. When an organization is willing to invest billions while also hiring professional skeptics, you should take both the ambition and the skepticism very seriously, which brings us to the biggest question of all. If commercial quantum advantage has not yet been proven, if today's machines are still extraordinary scientific instruments without a killer commercial application, then why are governments and trillion-dollar companies investing billions of dollars? The answer has been waiting for us since the opening scene of this film. It is time to return to the vault, to the theft you cannot see, and to uncover the money, the fear, and the solution. Chapter 17, The Vault. Now, let's return to the opening scene of this film, the stolen secrets, the silent theft, the attackers who cannot read what they steal. By now, you understand every piece of that puzzle. So, let's open the vault. Modern civilization relies on 2 different kinds of digital locks. The first is called Symmetric encryption. Systems like AES. Here, both sides already share the same secret key. Think of it like two people holding identical copies of the same house key. Against this kind of encryption, quantum computers have only one major weapon: Grover's algorithm. But as we learned in Chapter 13, Grover provides only a square root speedup, and the defense is surprisingly simple. Just use a longer key, AES 256, instead of AES 128. Problem solved. Symmetric encryption survives the quantum age with a relatively inexpensive upgrade. That is important to remember because it means many of the terrifying headlines are already only half true. The second type of lock is far more important and far more vulnerable. This is public key cryptography, RSA, elliptic curve cryptography, Diffie-Hellman key exchange. These are the mathematical tools that allow two complete strangers to create a shared secret over an internet connection, even while someone is listening. Every time you tap pay, every time you log into your bank, every time you visit a secure website, your phone and the server perform a remarkable handshake they have never met before. Yet within milliseconds, they agree on a brand new secret key. Only then does the fast AES encryption begin protecting your actual data. That familiar padlock icon in your browser depends on this process. Digital signatures, software updates, government certificates, bank transactions, almost all of them depend on the same mathematics. And those mathematical problems, factoring and discrete logarithms, contain exactly the kind of hidden rhythm that Shor's algorithm was designed to detect. A large, fault-tolerant quantum computer does not weaken these locks. It removes them completely. Now, the opening scene makes perfect sense. Imagine an attacker recording encrypted internet traffic today. They cannot read it, not yet, so they simply save everything. The encrypted handshake, the encrypted messages, the entire conversation. Then they wait. Years later, when a sufficiently powerful quantum computer exists, they replay those recordings, break the handshake, recover the secret key, and suddenly, everything becomes readable. Even conversations recorded decades earlier. This strategy has a name. Harvest now, decrypt later. It is not science fiction. It is real. Governments around the world already plan for exactly this scenario. The concern is not only military secrets. Think about what else remains valuable for decades. Medical records, scientific research, corporate intellectual property, private legal documents, and perhaps most importantly, the identities and communications of journalists, activists, and political dissidents living under governments willing to wait patiently for the key. If information encrypted today must remain secret, 15 years from now, there is a serious possibility that it is already living on borrowed time. Cryptographer Michel Mosca summarized the entire problem with one simple equation. Take the number of years your information must remain secret. Add the number of years it will take your organization to upgrade its security. If that total is greater than the number of years remaining before a cryptographically relevant quantum computer arrives, then you are already too late. It sounds simple, but history makes the second number painfully large. Major cryptographic migrations often take 10 years or even longer. That raises the obvious question. When will that quantum computer actually exist? Nobody knows. Researchers even have names for the milestone, a cryptographically relevant quantum computer, or CRQC, and the day it arrives is often called Q-Day. No one knows when Q-Day will come. Expert surveys generally place it somewhere in the 2030s. But those are forecasts, not guarantees. Forecasts can be wrong. In fact, Michel Mosca himself estimated back in 2015 that there was roughly a 1 in 7 chance RSA 2048 would be broken by 2026. That year has now arrived. RSA still stands. He also estimated about a 50% chance by 2031. Perhaps that prediction will prove correct. Perhaps not. The lesson is not panic, and it is not blind optimism. The lesson is preparation. Fortunately, there is already a solution. It is called post-quantum cryptography. Despite the name, it does not require quantum computers. Instead, it uses entirely new mathematics, new digital locks, built from problems that, as far as anyone knows, contain no hidden rhythm for Shor's algorithm to exploit. The leading family is based on lattices that I'll imagine an endless three-dimensional grid. Now, stretch it, twist it, bend it, then extend it into hundreds of dimensions, far beyond anything human intuition can visualize. Your secret is hidden as one specific point inside that unimaginably vast structure. Finding it becomes a geometric search through an enormous landscape with no repeating pattern, no rhythm, no hidden beat, nothing for quantum interference to lock onto. That is the key idea, although honesty requires one important reminder. No one has mathematically proven these problems are impossible to solve. Their security rests on decades of failed attempts, exactly the same foundation that protected RSA for almost half a century. To prepare for the quantum era, the United States Standards Agency, NIST, launched one of the largest cryptographic competitions ever held. Beginning in 2016, research teams from around the world submitted new post-quantum algorithms. 82 candidates entered. Then the global cryptography community spent years trying to destroy them, and many failed spectacularly. One finalist, called Rainbow, was broken in 2022 using nothing more than a laptop. Another promising candidate, called Psych, survived several rounds only to collapse after two Belgian researchers used a decades-old mathematical technique to break it in about an hour on a single desktop computer. Years of work gone before lunchtime. As painful as that sounds, it was exactly what the competition was designed to do. Better to discover weaknesses during testing than after deployment. In August 2024, the winners were officially announced. ML-Chem, formerly known as Kyber, became the new standard for key exchange. ML-DSA, formerly dilithium, became the standard for digital signatures. SLH-DSA provided a conservative hash-based backup. In 2025, NIST selected another key exchange algorithm called HQC from an entirely different mathematical family. Not because Kyber had failed, but because diversity is a form of security. If one mathematical foundation is ever broken, the others can still stand. And here's the part that surprises most people. This transition is no longer a future plan. It has already begun, quietly, without headlines, without most users ever noticing. Google Chrome and much of the internet's infrastructure began deploying hybrid post-quantum encryption during 2023 and 2024. Signal upgraded its protocol in 2023. Apple introduced post-quantum protection for iMessage in 2024. Every day, millions of people already use these systems without realizing it. Governments around the world are aiming to complete much of the migration by around 2035. The word hybrid matters. It means the old cryptographic lock and the new post-quantum lock are used together. An attacker must break both. Even if one system fails, the other continues protecting the data. Engineers even have a name for designing systems that can easily switch to new algorithms in the future. They call it crypto agility. Because history has taught us one important lesson. This will not be the last great cryptographic migration. But do not mistake already underway for easy. Because the hardest part of this transition is not the mathematics, it is something far more ordinary, finding where the old cryptography actually lives. Most organizations cannot answer that question. Encryption is buried inside forgotten software, inside decades-old hardware, inside network equipment, industrial machines, medical devices, vendor firmware, and computer code that nobody has touched in years. You cannot replace what you cannot even find. That, more than any mathematical challenge, is why this migration will take years. The new cryptographic systems also come with practical costs. Their public keys are much larger. An elliptic curve public key might be only 32 bytes. A post-quantum replacement can easily exceed 1 kilobyte. That means larger handshakes, more network traffic, and older networking equipment sometimes struggles to handle the extra data. Engineers deploying these systems have documented these problems in real-world networks. None of them are impossible, but every one adds time. History tells the same story. Even retiring the old SHA-1 hash function after weaknesses were already known took well over a decade, not because engineers lacked the replacement, but because replacing purity across an entire planet is simply slow. Slow is normal, which is exactly why starting early matters so much. There is another clock quietly ticking, and in some ways it is even more dangerous. Harvest now, decrypt later threatens confidentiality. It risks exposing today's secrets years from now. Digital signatures face a different danger: future forgery. Imagine a car, a satellite, a pacemaker, an industrial control system, a device built today, but expected to operate for 20 or even 30 years. Its software updates must always be verified. If the signature algorithm embedded inside that device is broken halfway through its lifetime, an attacker does not merely read its secrets. They can pretend to be the manufacturer. They can create fake software updates that appear completely legitimate. That is why the deepest deadline of the quantum transition is hidden inside firmware, secure hardware, and the roots of trust built into today's devices. Some products must be designed with post-quantum signatures from the very beginning, because years later, there may be no opportunity to upgrade them. There is one more system whose keys are already visible to the entire world: cryptocurrencies, Bitcoin, Ethereum, and many others. These systems protect ownership using elliptic curve digital signatures, exactly the type of mathematics that Shor's algorithm targets. Researchers estimate that roughly 1/4 of all Bitcoin, including many of the oldest coins, already sits in addresses whose public keys have been permanently exposed on the blockchain. To a future, cryptographically relevant quantum computer, those addresses could resemble a vault with the combination written on the front door. But once again, the full picture is more balanced. Mining itself depends primarily on hash functions. And as we learned earlier, Grover's algorithm only provides a limited speedup there. Modern Bitcoin addresses also reveal their public keys only briefly while a transaction is being processed, and both Bitcoin and Ethereum communities are already discussing post-quantum upgrades. Still, cryptocurrencies face one challenge that banks do not. Banks can replace lost credentials. Blockchains cannot. If the owner of an old wallet has disappeared forever, no one can rotate those keys. Whatever happens on Q-Day, those ancient coins will still be there, waiting. There is another defense, one that does not rely on new mathematics at all. Instead, it relies on quantum physics itself. It is called quantum key distribution, or QKD. Back in 1984, Charles Bennett and Gilles Broussard realized something remarkable. The no-cloning theorem could become a security system. If a secret key is encoded onto individual photons, then any eavesdropper must measure those photons to read them. But measurement always disturbs the quantum state. The attacker cannot copy the photons without leaving evidence behind. The communication channel itself becomes a burglar alarm. Its security is not based on difficult mathematics. It is based on the laws of physics. This is not theoretical. It already exists. In 2017, China's Meteosat satellite used quantum communication across approximately 1,200 kilometers. It successfully secured an intercontinental video call between Beijing and Vienna, a genuine milestone. But again, honesty requires the fine print. Quantum key distribution needs specialized hardware. It usually requires dedicated communication links. Long-distance operation remains difficult until practical quantum repeaters mature, and QKD protects only the encryption key itself. Your computers, your servers, and user authentication must still be secured by conventional methods. For these reasons, even organizations like the NSA and Britain's intelligence agencies recommend post-quantum cryptography as the practical solution for most of the world, quantum physics for a few, new mathematics for billions. Now, step back and look at the bigger picture. What is actually at stake? If one nation or one organization builds a cryptographically relevant quantum computer before the world's security systems finish migrating, it could quietly unlock decades of previously collected encrypted information, not by stealing new secrets, but by reading old ones. Diplomatic messages, scientific research, military intelligence, corporate archives, an intelligence advantage unlike anything in modern history. That possibility is one of the biggest reasons governments continue investing billions of dollars into quantum computing. It also raises difficult questions. Who upgrades first? Whose secrets remain protected? Who's become exposed? And who decides how that power should be used? Yet perhaps the strangest truth is this: if the migration succeeds, most people will never notice. Your browser will still display the same padlock icon. Your banking app will look exactly the same. Your messages will send exactly as before. No dramatic headlines, no visible celebration. The greatest cybersecurity upgrade in history may feel like nothing happened at all. And that would be the perfect outcome. Because in the end, the future of the world's secrets may depend less on spectacular quantum laboratories and far more on ordinary software updates, careful engineering, and millions of systems being upgraded before it is too late. But remember, breaking codes was never the dream that created quantum computing. It was only the fear that funded it. The original dream was something far more hopeful: to understand nature itself, to understand molecules, to build medicines, to discover materials that classical computers could never fully describe. It is finally time to return to Richard Feynman's original vision. Chapter 18, Speaking Molecule. Every molecule in existence is, in Feynman's words, a tiny quantum computer, running one program, itself. And inside every molecule, electrons exist in superposition. They become entangled, they interfere with one another. And from that hidden quantum dance come the properties that shape our world. How tightly a drug binds to its target, how a catalyst speeds up a chemical reaction, why a battery slowly loses capacity, or why one material conducts electricity while another becomes a superconductor. To predict these behaviors, today's computers must imitate that quantum dance. But as we learned earlier, every additional electron makes the calculation dramatically harder. The amount of information grows exponentially. Eventually, the simulation becomes too large for even the world's fastest supercomputers. Ironically, that is exactly where chemistry becomes the most interesting. Before we go further, one important truth. Because this subject is often exaggerated, classical computational chemistry is already an incredible success. Methods such as density functional theory, or DFT, have been refined for more than 50 years. Today, they accurately solve an enormous range of real chemical problems. They are fast, reliable, and they are not going away. Quantum computers are not replacing them. Instead, they aim to solve the problems where classical approximations begin to fail. Scientists call these strongly correlated systems. These are molecules where many electrons become so deeply entangled that no classical shortcut can describe them accurately. And with remarkable irony, these are often the molecules behind the most important chemical reactions on Earth. The most famous example is a molecule called Phi-MoCo. It sits at the heart of an enzyme known as Nitrogenase. This enzyme performs something humanity still struggles to do efficiently. It breaks apart nitrogen from the air and turns it into the building blocks of fertilizer. Our industrial method, the Haber-Bosch process, needs extremely high temperatures, enormous pressures, and consumes roughly 1 to 2% of all the energy used by humanity. Yet bacteria accomplish the same task, quietly, at room temperature. Scientists believe the secret lies inside Phi-MoCo, a cluster of iron and molybdenum atoms, whose electrons become so strongly entangled that today's classical methods reach their limits. A future fault-tolerant quantum computer, using the phase estimation technique we discussed earlier, could calculate this molecule's energy with far greater accuracy. If we truly understand how nature performs this reaction, we may eventually build an industrial catalyst that does the same. That possibility remains a future goal, not a guarantee, but if achieved, it could transform both agriculture and global energy consumption. The same story appears again and again. Better batteries, cleaner industrial catalysts, carbon capture materials, more efficient chemical manufacturing, each depends on understanding complicated quantum behavior among electrons, and each could benefit from more accurate quantum simulations. Perhaps the most famous mystery is high-temperature superconductivity. Discovered in 1986, it still has no complete explanation. Some materials carry electricity with almost no resistance, at temperatures far warmer than scientists expected. No existing theory fully explains why. If quantum simulations eventually reveal the mechanism, researchers might one day design superconductors that work near room temperature. Imagine electrical grids with almost no energy loss, or MRI machines that become dramatically cheaper. That possibility is exciting, but it remains speculation. The mystery is real. The solution is still unknown. Medicine deserves special attention because you will often hear headlines saying, "Quantum computers will cure cancer." That is simply not true. Drug discovery is a long process. Finding targets, designing molecules, laboratory testing, safety studies, clinical trials, and years of biological research. Quantum computers can improve one important stage, predicting how molecules interact and which candidates are most promising. That could save years of work and eliminate many failed ideas early. But they do not replace biology, and they do not magically produce cures. Their promise is simpler, fewer dead ends, and faster discoveries. When might all of this happen? Realistically, these breakthroughs require fault-tolerant quantum computers, machines with thousands of reliable logical qubits. The kinds of systems we discussed in the previous chapter. Today's hardware can only simulate very small molecules, such as hydrogen or lithium hydride. These are valuable demonstrations, but they are still proof-of-concept experiments. Whether today's noisy quantum computers can deliver useful commercial chemistry remains an open question. One more misconception deserves clearing up. Quantum computers are not expected to revolutionize climate modeling. Climate simulations are dominated by classical fluid dynamics, a task that today's supercomputers already handle extremely well. The real climate impact of quantum computing is likely to come somewhere else. Better batteries, better fertilizers, better catalysts, better carbon capture materials, indirect benefits that could still be enormous. Finally, a fascinating side story: quantum biology. Some researchers once believed photosynthesis relied on long-lived quantum effects. Later experiments suggested more ordinary explanations. Another idea, that migratory birds navigate using quantum-sensitive chemistry inside their eyes, remains actively studied. It is intriguing, possible, but not yet proven. Interesting science, not established fact. So why invest decades and billions of dollars into quantum chemistry? Because chemists estimate that the number of possible drug-like molecules is around 10 to the power of 60, a 1, followed by 60 zeros. Everything humanity has ever created is only a tiny fraction of that unimaginable landscape. We have explored it with candles. A quantum computer promises something very different. Not a candle, a lighthouse. And throughout history, lighthouses have almost always repaid the effort it took to build them. But chemistry is the patient reward, the payoff expected years from now. Today's excitement is chasing something faster. Financial markets, artificial intelligence, optimization. Some of those promises are real. Many are not. The next chapter separates the science from the hype and answers one of the biggest questions of all. What will quantum computers never be able to do? Chapter 19, Money, Minds, and What Will Never Change. Two technological revolutions are unfolding at the same time: quantum computing and artificial intelligence. Naturally, people ask one question: will these two technologies merge? The honest answer is yes and no. There are two very different directions. And by the end of this chapter, we will answer one of the biggest questions in this entire documentary. What will quantum computers never replace? First, quantum computing for AI. This is where reality and headlines often drift apart. As of the mid-2020s, no quantum computer has demonstrated a clear advantage on any real-world machine learning task. Despite thousands of headlines, the evidence simply is not there. Why? Because the obstacles are built into the problem itself. First, most AI begins with enormous amounts of classical data. Getting that data into a quantum computer can take so much work that it cancels out much of the potential speedup. Second, several famous quantum AI algorithms were later matched by clever classical algorithms. Remember Ewan Tang from the previous chapter? Her work showed that some celebrated quantum advantages disappeared once classical researchers found better methods. And third, training quantum machine learning models faces another challenge. Researchers call it a barren plateau. Imagine hiking across a perfectly flat desert. No hills, no valleys, no clues about which direction leads upward. The learning process becomes almost blind. None of this proves that quantum AI is impossible. Researchers continue exploring areas where the data itself is naturally quantum, such as information coming directly from quantum sensors or quantum simulations. Those applications may eventually reveal genuine advantages. But today, the honest label is simple: interesting, unproven, and often overhyped. Now, the second direction: AI helping quantum computing. This partnership is already real. Artificial intelligence is improving quantum computers today. Machine learning systems help identify and correct errors. They calibrate delicate qubits, they optimize microwave pulses, they improve chip layouts, and they learn to recognize tiny sources of noise that humans might miss. One notable example arrived in 2024. Google DeepMind introduced AlphaQubit, an AI system that improved quantum error correction by outperforming several traditional decoding methods. So for now, the relationship is mostly one way. Artificial intelligence is helping raise the quantum computer, not the other way around. One quick note about energy. People sometimes claim quantum computers will become green AI. That comparison is misleading. Quantum computers and AI data centers solve completely different problems. They are not competitors, and one cannot simply replace the other. Now, finance. Wall Street is famous for chasing every possible advantage. Is quantum computing useful there? Potentially, yes. Many financial calculations rely on something called Monte Carlo simulation. Instead of solving one problem, the computer simulates millions of possible futures, then averages the results. Quantum algorithms contain a technique called amplitude estimation, which can perform this type of calculation with a proven quadratic speedup. That is established mathematics, but there is an important condition. These algorithms require large, fault-tolerant quantum computers, machines that do not yet exist. So today's banks are mostly experimenting, preparing, learning, investing in research, not generating profits with quantum computers, at least not yet. Next comes one of the most advertised applications: optimization, planning airline schedules, routing delivery trucks, managing supply chains, packing shipping containers. This is where marketing often races ahead of reality. The honest answer is straightforward. Today's best classical optimization software still wins, every time. Quantum methods, including QAOA and quantum annealing, remain promising research tools. Sometimes they produce interesting results. But no quantum system has yet shown a clear commercial advantage over the best classical solutions. Once those classical systems are fully optimized, remember what we learned earlier. Most optimization problems simply do not contain the hidden mathematical structure that quantum algorithms need. No rhythm, no repeating pattern, nothing for quantum interference to amplify. So whenever someone promises exponential speedups for logistics today, be skeptical. The evidence is simply not there. Other industries, including manufacturing, space exploration, and engineering, are likely to benefit far more from quantum simulation and new materials than from optimization alone. And now, the promise we made at the beginning of this documentary, the list of things quantum computers will never replace. Not, probably not, maybe someday, never. Because the limits come directly from the laws of physics. Quantum computers will not replace your laptop or your phone. They will not replace email, web browsing, streaming video, word processing, spreadsheets, databases, social media, or almost every video game you have ever played. Why? Because these tasks contain no hidden quantum structure, no repeating rhythm, no special pattern, nothing for quantum interference to exploit. And every answer produced by a quantum computer must still pass through measurement, where all that rich quantum information collapses into ordinary classical bits. Input is expensive, output is expensive, and every quantum operation costs vastly more than flipping a transistor inside today's processors. Even with future improvements, that basic reality does not change. Running a spreadsheet on a quantum computer would be like using a billion-dollar scientific laboratory to perform arithmetic slower than a calculator from the 1970s. So here's the right way to think about quantum computers. They are not faster versions of today's computers. They're completely different instruments. Think of a wind tunnel. Think of a telescope. Think of an MRI scanner. Each exists for one purpose: to answer questions that ordinary tools cannot answer. Nobody expects a telescope to write emails. Nobody complains that an MRI cannot browse the internet. Quantum computers belong in that same family. The analogy is not perfect. Unlike a telescope, a quantum computer is programmable. The same machine can tackle chemistry, cryptography, material science, and many other specialized problems. It is an instrument with a keyboard. So how will most people actually use one? probably the same way they already use supercomputers. Through the cloud, quantum processors will remain inside highly specialized laboratories, surrounded by classical CPUs and GPUs. Whenever a rare calculation truly needs quantum power, the request will travel across the internet, run on the quantum hardware, and return the result. Much like hospitals share one MRI machine instead of placing one inside every home. The quantum future is unlikely to sit on your desk. Instead, it will quietly improve the products, medicines, materials, and security systems you use every day, often without you even noticing. And while the world waits for quantum computers to mature, another branch of quantum technology has already arrived. These machines are guiding submarines, mapping the human brain, detecting gravitational waves from black hole collisions, and they succeed because of the very same quantum sensitivity that makes quantum computers so difficult to build. Their story is next, and it may be the most overlooked success in the entire quantum revolution. Chapter 20, The Quiet Revolutions. In the last chapter, we saw the greatest weakness of a quantum computer. A tiny amount of heat, a small vibration, or a faint magnetic field can disturb a qubit. At first, that sounds like a flaw, but here's the twist. If a quantum system is sensitive to almost everything, then it can also become an incredibly powerful sensor. The very weakness that makes quantum computers difficult to build becomes the greatest strength of quantum sensing. And unlike quantum computing, this technology is not waiting for the future. It is already here. Let's begin with the quantum machine that quietly runs much of modern life, the atomic clock. Since 1967, the official definition of 1 second has not come from the Earth's rotation or from a mechanical clock. Instead, it is defined by a natural rhythm inside the cesium atom. Exactly 9,192,631,770 oscillations. Because every cesium atom is identical, every atomic clock keeps exactly the same rhythm. Today's most advanced versions, called optical atomic clocks, are so incredibly precise that they would lose less than a single second over the entire age of the universe. That is not science fiction. It is established laboratory fact. You rely on this technology every single day. GPS exists because satellites carry atomic clocks. Each satellite continuously broadcasts the exact time. Your phone compares those tiny differences, measured in billionths of a second, to calculate your position. But there is another remarkable detail. Einstein's theory of relativity predicts that clocks in orbit tick slightly faster than clocks on Earth, about 38 millionths of a second, every day. That tiny difference sounds insignificant, but if engineers ignored it, your GPS position would drift by several kilometers every single day. So every time the blue dot appears on your map, it is being held in place by both quantum physics and Einstein's relativity, quietly, constantly, without most of us ever noticing. Atomic clocks also synchronize power grids, financial markets, telecommunications, and the internet itself. Modern civilization literally runs on precise quantum time. The same technology is now reaching beyond Earth. NASA has already tested a deep space atomic clock in orbit. Its goal is simple: allow future spacecraft to navigate deep space on their own without constantly waiting for instructions from Earth. Researchers are also developing quantum gravity centers for satellites to monitor glaciers, groundwater, and changes in Earth's climate with extraordinary precision. Now imagine something different. Suppose GPS disappears, perhaps underground, deep underwater, or during a conflict where satellite signals are blocked. How do you navigate then? The answer may come from atom interferometry. Scientists cool atoms to temperatures just above absolute zero. Then they split each atom's matter wave, allowing it to travel along two different paths. When those paths reunite, they create an interference pattern, exactly like the quantum interference we explored earlier. From that interference, scientists can measure movement, rotation, and acceleration with astonishing precision. A vehicle equipped with this technology could determine its position without receiving any external signal. No satellites, nothing to jam, nothing to spoof. Quantum navigation has already reached sea trials and commercial flight demonstrations. The technology is real. The engineering continues. Point those same quantum sensors toward the ground and they become gravity cameras. Every underground object, whether rock, water, or empty space, changes gravity ever so slightly. Quantum gravimeters can detect those tiny differences. In 2022, researchers at the University of Birmingham successfully detected a buried tunnel under real outdoor conditions without digging. Potential future applications include locating underground pipes, finding hidden archaeological sites, tracking groundwater, and even monitoring volcanic activity. Quantum sensors are also transforming medicine. Special magnetic sensors, called optically pumped magnetometers, can detect the incredibly weak magnetic fields produced by your brain. Unlike older scanners, patients can move naturally during the scan. That makes the technology especially valuable for children and for diagnosing epilepsy. Meanwhile, diamond-based quantum sensors, built around tiny atomic defects, can measure magnetic fields with extraordinary precision. Scientists are already using them to study living cells and even detect electrical currents inside computer chips. Perhaps the most breathtaking example comes from astronomy. The LIGO observatories, which detect gravitational waves from colliding black holes, have improved their sensitivity using a remarkable quantum technique. It is called squeezed light. Scientists reshape quantum uncertainty itself, reducing the type of noise that limits their measurements. The result? Humanity can now detect more black hole collisions than before. Think about that for a moment. Engineered quantum states are already expanding our view of the universe. Quantum sensing is no longer a promise. It is already changing science. Of course, every powerful technology creates new questions. Sensors capable of seeing through the ground may eventually raise privacy concerns. Highly sensitive magnetic detectors could one day challenge military stealth technologies, including submarines. These possibilities remain uncertain, but they remind us that society should discuss new technologies before they become widespread, not afterward. There is one more quiet revolution, not quantum computers, quantum networks. Instead of sending ordinary information, these networks send something far stranger: entanglement itself. Why build such a network? 4 reasons. First, security. Quantum key distribution, which we explored earlier. Second, scale. Future quantum computers will almost certainly be built from many smaller quantum processors connected together. Third, privacy. A remarkable idea called blind quantum computing allows a remote quantum computer to perform calculations without learning either your data or even the question you asked. That has already been demonstrated on a small scale. And finally, the distant future. Scientists imagine networks of entangled telescopes acting together as one giant Earth-sized instrument, or global networks of ultra-precise clocks keeping time together with unprecedented accuracy. These remain future possibilities, but the foundations are already being explored. At the center of every quantum network is one of the most misunderstood ideas in physics: quantum teleportation. Despite the name, nothing physical is transported, no person disappears. No object travels through space, only the quantum state, the information, moves from one particle to another. The process consumes one entangled pair, like using up a battery. It also requires 2 ordinary classical bits to complete the transfer. Without those classical bits, teleportation simply cannot happen. Nothing travels faster than light. The original quantum state is destroyed during the process. The no-cloning theorem guarantees that only one copy ever exists. Quantum teleportation is information relocation, not duplication, and certainly not science fiction teleportation. Scientists first proposed the idea in 1993, demonstrated it in 1997, and in 2017, teleported a quantum state from Earth to China's Michia satellite over a distance of roughly 1,400 kilometers. One final obstacle remains before a true quantum internet becomes possible: the quantum repeater. Today's internet extends signals by copying information over and over again. But quantum information cannot be copied. Physics forbids it. So quantum repeaters must work in an entirely different way. They temporarily store entanglement, then carefully connect shorter links into much longer ones, without ever measuring the quantum information itself. Today, these devices remain experimental, but progress continues. Researchers have already demonstrated small quantum networks, distributed entanglement through commercial optical fiber, and begun building metropolitan-scale quantum links. The comparison to the early internet is tempting. A handful of connected nodes, many competing ideas. No one yet knows what the final network will become. But there is one crucial difference. The classical internet was built by copying information. The quantum internet must succeed without ever copying it. So, where are we now? Atomic clocks, quantum navigation, gravity imaging, brain scanners, quantum networks. None of these technologies require fully fault-tolerant quantum computers. Many already exist, and together they are quietly reshaping science, medicine, navigation, and national security. Which brings us to the next chapter. Because at this point, science is no longer the only story. Now, governments, militaries, and trillion-dollar companies enter the race, and the amounts being invested are extraordinary. Chapter 21, The Race. In January 2025, at the CES Technology Show in Las Vegas, one sentence shook the entire quantum industry. Jensen Huang, the CEO of NVIDIA, the company whose chips power today's artificial intelligence revolution, said something simple. He suggested that truly useful quantum computers were probably 15 to 30 years away. That was it. Not a warning, not a prediction of failure, just one reasonable estimate that many experts would have agreed with. The market reacted instantly. Quantum company stocks lost around 40% of their value in a single day. Billions of dollars disappeared, almost overnight. Just 2 months later, NVIDIA hosted its own Quantum Day at its annual conference. Huang walked onto the stage, smiled, and joked that it might be the first event in history where a CEO invited guests to explain why he was wrong. The joke landed, but it revealed something much deeper. A market built on promises decades into the future is incredibly fragile. Sometimes one honest sentence is enough to move billions of dollars. And that tells you something important. Whenever you read a quantum computing headline, always ask yourself, is this science, or is someone selling a future? So why is the excitement so enormous? Because governments are spending money as if this were another space race. Public investment in quantum technology has now reached somewhere between $40 and $55 billion worldwide. The exact number is uncertain because some governments publish detailed budgets and others reveal almost nothing. China remains the biggest mystery. Its massive national program is centered around Hefei, the Michis quantum satellite, and quantum machines like Zhuzhang and Zuchongji, which continue competing with Western systems on benchmark experiments. How much China is actually spending, nobody outside the country knows for certain. The often quoted figure of $15 billion is an outside estimate, not an official number. The United States answered with its own investments. The National Quantum Initiative began in 2018. Since then, multiple government agencies have expanded funding. DARPA launched the Independent Quantum Benchmarking Initiative, designed specifically to separate real progress from hype. And beginning in 2024, the US introduced export controls on advanced quantum technologies, placing them alongside strategically important technologies like advanced semiconductors and jet engines. Around the world, the race continues. Europe supports a €1 billion flagship program alongside major national investments from Germany and France. The United Kingdom committed roughly £2.5 billion over a decade. India launched its own national mission. Australia invested heavily in PsiQuantum's Brisbane facility. Japan, Canada, Israel, Singapore, South Korea, and several Gulf nations have all launched their own quantum strategies. Countries do not invest this kind of money in scientific curiosities. The corporate race has its own two levels. At the top are the technology giants, IBM, Google, Microsoft, Amazon, Intel, and NVIDIA. For them, quantum computing is becoming another pillar of cloud computing. Amazon even introduced its own error correction-focused quantum chip in 2025. NVIDIA took a different path. Instead of building quantum computers directly, it supplies the powerful classical computers that every quantum laboratory depends on. It's a smart strategy. If quantum succeeds, NVIDIA wins. If quantum takes longer than expected, NVIDIA still wins. Around those giants orbit the specialist companies Quantinuum, valued at roughly $10 billion after its 2025 funding round. IonQ, reported in early 2026 as the first quantum company to generate more than $100 million in annual revenue. Alongside them, Rigetti, Quantum, Quera, Pascal, Alice and Bob, Xanadu, and dozens of ambitious startups are all betting that their approach becomes the future. But remember what happened after Jensen Huang's comment. Their fortunes can rise or fall with a single sentence. Money, however, is not the only scarce resource. People are. Industry surveys consistently report far more open positions than qualified experts. The shortage isn't just hardware, it is talent. And for anyone considering a career in this field, that shortage may become one of its biggest opportunities. There is another challenge, one that deserves attention before these machines become truly powerful. Quantum technology is a classic dual-use technology. It promises extraordinary benefits, but it also creates extraordinary risks. The first nation to build a cryptographically relevant quantum computer could gain an unprecedented intelligence advantage. As post-quantum security rolls out, wealthier organizations will upgrade first, while poorer institutions remain vulnerable. And if quantum breakthroughs transform medicine, materials, or energy, the gap between countries could become even wider than today's digital divide. International rules are still in their infancy. The best time to debate them is before the technology fully arrives. Before we leave this chapter, one final milestone deserves recognition. The United Nations declared 2025 the International Year of Quantum Science and Technology. Exactly 1 century after a young Werner Heisenberg, working through illness on the isolated island of Helgoland, helped launch quantum mechanics. In just 100 years, humanity has traveled from abstract equations to logical qubits and global quantum networks. Whatever happens next, that journey alone is one of science's greatest stories. But every great race creates noise, and where there is noise, there is misinformation. Before this documentary ends, there is one final gift to give you. A simple way to judge any quantum computing claim you ever hear, so that within a minute, you can tell the difference between genuine science and clever marketing. Chapter 22, The Myth Court. 8 myths, 8 verdicts. By now, you already have every tool you need to judge them. So let's put them on trial. Myth number 1. A quantum computer tries every possible answer at once. This is the most famous myth in quantum computing, and it's so convincing because it is almost true. A quantum computer really does explore many possibilities at the same time, but when you measure it, you get only one result. Not all of them. The real power isn't in trying everything, it's in interference, carefully increasing the chances of the right answer while canceling the wrong ones. And interference only works when the problem has the right kind of hidden structure. Here's the simplest proof. If a quantum computer could truly brute force every possibility, then Grover's algorithm would never have been needed. But Grover proved something remarkable. For an unstructured search, the absolute best quantum speedup is only the square root. That isn't an opinion, it's mathematics. Verdict, false. And understanding why it is false may be the single most important lesson in this entire documentary. Myth number 2. Quantum computers will replace ordinary computers. They won't. A quantum computer is not a faster laptop. It is a specialized scientific instrument, like an MRI scanner or a telescope. It solves a very small class of problems that ordinary computers struggle with. For almost everything else, your phone, your laptop, and future classical computers remain the better choice. Verdict, permanently false. Not because of today's technology, but because of the underlying physics and economics. Myth number 3, entanglement lets us communicate faster than light. It does not. Entangled particles share remarkable correlations, but neither side can send information on its own. Until an ordinary message traveling no faster than light arrives to compare results, both observers simply see random outcomes. Quantum mechanics itself forbids faster than light communication. Einstein's speed limit still stands. Verdict, false. Myth number 4. Quantum computers will solve every hard problem. They won't. Many famous problems, such as perfectly optimizing routes, schedules, or other NP-complete problems, are still believed to remain extraordinarily difficult, even for quantum computers. Quantum machines are brilliant specialists, not universal problem solvers. Verdict, false. Anyone promising exponential speedups for everything is selling fantasy. Myth number 5. Quantum physics explains consciousness and powers my healing bracelet. Let's separate science from marketing. The idea that consciousness may involve quantum effects is a genuine scientific hypothesis. It was proposed by Roger Penrose and Stuart Hameroff. But today, it remains speculative, and most physicists and neuroscientists are not convinced. As for products that advertise themselves as quantum wellness or quantum healing, they usually borrow impressive scientific words without any scientific evidence. Everything around you is already quantum. Your chair is quantum, your coffee is quantum, your socks are quantum. Putting the word quantum on a label proves absolutely nothing. Verdict, unproven at best. At worst, it's just expensive marketing. Myth number 6. Quantum computers are all hype, they'll never work. Unlike the previous myths, this one deserves respect. Serious scientists have argued it. Mathematician Gil Kalai has suggested that quantum noise may become fundamentally correlated, breaking the assumptions behind error correction. That is a legitimate scientific concern, not internet skepticism. But today's evidence points in the opposite direction. Multiple research groups have already demonstrated below-threshold error correction. Logical qubits now outlive physical ones, and experimental results increasingly follow what the mathematics predicted decades ago. Could a hidden obstacle still appear? Yes, absolutely. And discovering such a limit would itself transform physics. But today, the evidence favors progress. Verdict, a serious minority position, currently losing on the evidence. Myth number 7. Q-Day is almost here. Banks will collapse next year. No, today's real quantum computers have honestly factored only very small numbers. The gap between those demonstrations and breaking modern internet encryption remains enormous. But there is another side to the story. Cryptographic migrations take many years. Some information must remain secret for decades, so waiting until the last minute would be a mistake. The right response is neither panic nor complacency. It is preparation. Verdict. False as panic, true as a to-do list. And the next time you see a headline claiming RSA has finally been broken, ask 2 simple questions. How large was the number, and can the method actually scale? Myth number 8. More qubits automatically mean a better quantum computer. Not even close. A machine with 50 extremely accurate qubits can outperform another with 1,000 noisy ones. Quality matters more than quantity. Always. Remember the rule from earlier. Count the 9s, not the qubits. Verdict. False. Now, here's the most useful tool in this entire documentary. A 60-second checklist for judging any future quantum headline. Ask yourself, was the result published in peer-reviewed research or only announced in a press release? Can independent researchers verify the result or only the company itself? Have classical algorithms had a chance to compete? Are they talking about logical qubits or merely physical qubits? Is it a demonstrated achievement or simply a future roadmap? And finally, who benefits if you believe the headline? Ask those questions, and you will understand this field better than most news coverage ever will. One final word about timelines. Nobody knows exactly when a cryptographically relevant quantum computer will arrive. Expert surveys generally point toward the 2030s, but the uncertainty spans many years in both directions. These are forecasts, not laws of physics. So what should you watch? If error correction continues scaling successfully and commercially valuable quantum applications are independently verified, the optimists will look increasingly correct. If error rates refuse to improve, if correlated noise becomes an unavoidable barrier, or if decoding proves impossible at scale, the skeptics gain ground. Those are the signals that matter. Everything else is mostly noise. In the end, this entire documentary can be reduced to a single sentence. Quantum computing is 3 different things, sharing one name. First, established physics, supported by overwhelming experimental evidence. Second, unfinished engineering, making remarkable progress, but still facing enormous challenges. And third, uncertain economics where timelines, profits, and ultimate impact remain unknown. Most bad takes, whether wildly optimistic or deeply pessimistic, come from mixing those 3 together. Now you know how to separate them. Only 2 questions remain. The first is personal. Now that you understand quantum computing, should you be part of it? Chapter 23. Your move. Let's begin by tearing down the biggest barrier of all. You do not need a PhD in physics to work in quantum technology. Really, the scientific frontier certainly does, and that frontier is extraordinary. But every frontier eventually becomes an industry, and industries need far more than scientists. They need software engineers who build compilers, programming tools, and cloud platforms, control engineers who work with microwaves, lasers, and FPGAs, experts in cryogenics, vacuum systems, and chip fabrication. The people sometimes called the quantum plumbers, and the title is meant with complete respect because without them, nothing you've seen in this documentary would exist. The field also needs error correction researchers, materials scientists, product managers, teachers, writers, and policymakers. Quantum technology isn't short of ideas, it's short of people. Getting started costs almost nothing. Today's quantum tools are free. You can begin with familiar Python libraries like Qiskit, Cirq, Qsar, Pennylane, Amazon Breakit, or CUDA-Q. You write code using the same quantum gates you've already learned. A Hadamard, a CNOT, a measurement, you test everything on a simulator, and then something remarkable happens. You can upload that same program over the internet to a real quantum computer, not a simulation, a real machine. IBM first opened this opportunity to the public in 2016. Since then, anyone, almost anywhere, has been able to experiment with real quantum hardware. Think about that for a moment. A student sitting at home with an ordinary laptop can send instructions across the world to a quantum processor operating just a few thousandths of a degree above absolute zero. That is an astonishing privilege. You are the first generation in history that can do this. It almost feels wrong not to try it at least once. When you do, make it memorable. Your first quantum program can be incredibly simple, just 3 steps. Apply a Hadamard gate to create superposition. Use a CNOT gate to create entanglement. Then measure both qubits. Submit the program, wait for your turn in the queue, and somewhere, perhaps thousands of kilometers away, microwave pulses race into a quantum chip inside a giant dilution refrigerator near absolute zero. For a brief moment, the universe performs one of the strangest calculations it knows how to do, and it does it for you. The learning path is clearer today than ever before. There are free online courses, open textbooks, excellent documentation, open source communities, hackathons where complete beginners work alongside experienced researchers. The doorway has never been more open. Many people, however, still worry about the mathematics. So let's remove that fear too. At its heart, quantum computing is built on linear algebra. That sounds intimidating, but the basic ideas are surprisingly simple. A vector is simply a list of numbers. A qubit's amplitudes form a list of 2 numbers. A matrix is simply a table that transforms one list into another. Every quantum gate you've learned is nothing more than one of those tables. Finally, add complex numbers which you can picture as arrows that rotate, same rotating phase we've been discussing throughout this documentary. With those ideas, you stop relying on metaphors. You begin reading real quantum computing. For a motivated learner, that journey is measured in months, not decades. From there, many different backgrounds can lead into the field. Physics, computer science, electrical engineering, mathematics, chemistry, all of them matter. Universities around the world, including MIT, Caltech, Harvard, the University of Chicago, the University of Maryland, Waterloo, Oxford, Delft, ETH Zurich, UNSW, and the University of Science and Technology of China in Hefei have built major quantum programs, and every year, more universities join them. Before we finish, let me offer 2 pieces of advice, not as facts, as opinions. First, become excellent at one classical discipline and then learn quantum. The industry needs outstanding engineers who also understand qubits, not people who know only the buzzwords. Depth will always beat superficial expertise. Second, think carefully about timing. Learning quantum computing today feels a lot like learning classical computing in the mid-1960s. The machines already exist, but they're rare, powerful, expensive, and still waiting for their defining applications. No one then could fully imagine the personal computer, or the smartphone, or the internet economy. We may be standing at a similar moment now. And here's the reassuring part. Even if quantum takes longer than expected, the skills are never wasted. Cryogenics supports fusion research, control systems power robotics, error correction mathematics strengthens communications, programming engineering, and mathematics never go out of style. At worst, you become highly employable. Even if you never work in quantum technology, understanding it still matters. Managers, lawyers, teachers, journalists, policymakers, anyone helping society make decisions. They all benefit from knowing the difference between a physical qubit and a logical qubit, between a real breakthrough and a clever press release, between science and marketing. That kind of literacy is becoming a civic skill. Only one question remains. The question this entire documentary has been building toward. Forget the careers. Forget the investments. Forget the code breaking. Why does any of this matter? What changes when a civilization learns to compute using the deepest rules of reality itself? Chapter 24, The Century of the Qubit. Take one final journey with me. 100 years in a single breath. A careful physicist in Berlin discovers that energy comes in tiny packets and calls the idea an act of desperation. A young patent clerk takes that strange idea seriously and realizes that light itself comes in packets too. A Danish physicist places electrons on invisible ladders inside the atom. A French prince suggests that matter behaves like waves. Then, on a small windswept island, a young Werner Heisenberg, unable to escape his hay fever, works through the night and sees a completely new picture of reality. Max Born accepts probability. Albert Einstein refuses. John Bell turns that disagreement into mathematics. Decades later, experiments test Bell's idea again and again and again. Every time, nature gives the same answer. The strange correlations are real. Entanglement is real. Quantum mechanics survives. Then, Richard Feynman asks an extraordinary question. What if, instead of fighting quantum mechanics, we used it to compute? David Deutsch proves that such a machine could exist. Peter Shor discovers the hidden rhythm inside modern cryptography, and suddenly, an idea once discussed only by philosophers becomes a matter of national security. Then comes quantum error correction, the threshold theorem, and finally, within just the past few years, real quantum hardware begins crossing the line that mathematics predicted nearly 3 decades ago. Logical qubits appear. Errors shrink exactly as theory promised. 100 years from desperate equations to machines that compute with reality itself. Now step back and look at what these machines truly are. Every large quantum computer is more than a computer. It is also an experiment, perhaps the most demanding experiment ever performed on quantum mechanics itself. Every larger machine pushes superposition and entanglement into territory that no physicist has ever explored before. Most scientists expect quantum mechanics to continue working perfectly. So far, it always has. But if the theory hides some deeper limit, some unknown law, some undiscovered crack, these machines are where we are most likely to find it. Think about the beauty of that. If quantum computing succeeds, we gain revolutionary technology. If it unexpectedly fails because nature reveals an entirely new law of physics, we gain one of the greatest scientific discoveries in history. Either way, humanity wins. Few scientific journeys offer a wager like that. The philosophers still have their questions, David Deutsch argues, and this remains his interpretation, not established fact, that a large quantum computer may point toward the existence of many parallel worlds. His reasoning is simple. Where else could all those quantum computations be taking place? Most physicists are not convinced, but nearly all agree. The question itself became much sharper because quantum computers exist. And then there is Rolf Landauer's beautiful reminder. Information is physical. Computation was never abstract. It always lived inside physical objects. First, punch cards, then vacuum tubes, then silicon chips. For decades, we built computers using the classical rules of nature. Now, for the first time, we are learning to compute using nature's deepest rules instead. It is as though humanity has discovered that the universe owned a richer language all along, and we are only beginning to read it. Remember the vault from the opening of this documentary. Somewhere tonight, encrypted information is still being collected, stored, waiting. Its future now depends on a race. A race between quantum computers that do not yet exist and post-quantum security that is already being deployed. How that race ends will not depend only on physicists. It will depend on standards organizations, software updates, engineers improving tiny error rates, and ordinary people who became curious enough to help build the future. Perhaps people like you. If there is one image I hope stays with you, let it be this. Albert Einstein was wrong about quantum mechanics. Magnificently wrong. Productively wrong. His doubts forced scientists to ask harder questions. Those questions inspired better experiments. Those experiments confirmed stranger truths. And those truths became technology. Technology that may one day reshape medicine, energy, materials, and the security of the digital world. Science does not move forward because people are always right. Science moves forward because people are willing to be wrong openly, carefully, and honestly until nature answers. Somewhere, right now, a golden dilution refrigerator hums quietly in the dark. Inside it, colder than deep space itself, a handful of fragile qubits hold a quantum superposition for just a few precious moments, a tiny whisper of possibility. Perhaps that is the deepest lesson of quantum physics. The universe has been keeping its options open all along. Now, so can we. If this documentary helped you understand something new, consider subscribing. If you know someone who loves asking difficult questions, share this with them. They're exactly who this was made for. Stay curious, stay secure, and I'll see you in the next one.